Hello there, and welcome to the Cosmic Sleep Science. Tonight we drift into the wonders of the cosmos, a place so vast our minds can't even begin to comprehend it. Out there, far beyond our solar system, the universe is full of immense activity. For billions of years, entire worlds have been created and destroyed in a potentially infinite cosmic cycle. Astronomy offers a glimpse into this miraculous world where stars collide with unimaginable power. Planets drift through the endless darkness, and invisible forces warp the very fabric of reality. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, take a slow breath. Let your body soften and allow your mind to relax. Tonight we explore the most relaxing facts about astronomy, gentle truths that require nothing from you except to listen and let go. Let's begin. The light reaching your eyes from certain stars began its journey before humans walked the Earth. Consider how peaceful that is. A photon, a tiny particle of light, leaves the surface of a distant sun and travels through the emptiness of space for thousands upon thousands of years. It passes through nothing but silence and darkness, crossing distances so immense that our minds cannot truly grasp them. And then, on one particular night, it completes its journey by landing softly on this small blue planet. That ancient light asks nothing of you. It simply arrives, having traveled patiently across the cosmos, to meet your gaze for a single fleeting moment. There is something deeply calming about knowing that the night sky is filled with these patient travelers. Each star you see represents a beam of light that has been sailing through the void for an almost unimaginable length of time. Some of that light left its source when dinosaurs still roamed the Earth. Other beams departed even earlier, when our planet was young and covered in molten rock. The stars do not rush. They do not hurry their light toward any particular destination. They simply shine, sending their gentle glow outward in all directions. And some small portion of that glow eventually finds its way here. The universe expands so slowly that you would never notice it in a single lifetime. Every galaxy drifts away from every other galaxy at a pace that seems almost lazy when measured against the scale of human experience. Billions of years from now, the distances between cosmic structures will be greater than they are today. But right now, in this moment, everything remains essentially unchanged from last night, or the night before, or any night within your memory. The cosmos grows larger, with a patience that defies comprehension. There is no hurry out there among the stars. Everything unfolds according to rhythms far too slow and vast for any creature to witness in full. This gentle expansion means that space itself is stretching, carrying galaxies along with it. Like leaves floating on a slowly widening river, the motion is so subtle that even the most sensitive instruments can only detect it when observing objects billions of light years away. For everything closer, the expansion is essentially invisible. Your neighborhood of stars, your galaxy, your local group of galaxies, all of these remain bound together by gravity, drifting through an ever-growing universe, but staying connected to one another. There is comfort in knowing that this vast stretching happens so gradually that it will never disrupt the familiar patterns of the night sky during any human era. Some moons in our solar system possess underground oceans that remain liquid despite the incredible cold of outer space. These hidden waters lie beneath shells of ice, warmed by the gentle flexing of the moon's interior as it orbits its parent planet. No sunlight reaches these buried seas. No wind stirs their surfaces. They exist in absolute darkness and perfect stillness, yet they contain more liquid water than all the oceans of Earth combined. Somewhere beneath the frozen exterior of these distant worlds, water flows and circulates in silence, driven by forces that have persisted for billions of years. The thought of these quiet oceans can bring a sense of peace. They ask nothing of the universe. They simply exist, hidden away from the light of the sun, cradled by ice, and warmed by the slow pulse of gravitational energy. Whatever processes unfold in those depths happen without observation, without hurry, without any awareness of the cosmos beyond. These oceans have likely remained in this state for longer than complex life has existed on Earth. They will continue long after the present moment fades into history. Their patience is absolute, their stillness complete. The nearest star to our Sun takes more than 4 years to send its light here. That neighboring sun, a small red star, glows with a soft and steady light that poses no threat to anything. It simply burns through its fuel at a leisurely pace, releasing energy into the darkness around it. The light that left that star 4 years ago is only now arriving at Earth. During all those years of travel, that light passed through nothing but empty space, encountering no obstacles, reflecting off no surfaces, simply moving forward at a constant speed until it reached this small corner of the galaxy. When you consider the scale of this journey, even our closest stellar neighbor seems impossibly far away. And yet that distance also means safety. The vast emptiness between stars ensures that events in one solar system rarely affect events in another. Each star exists in its own bubble of isolation, separated from its neighbors by years of travel, even at the speed of light. This cosmic solitude might seem lonely, but it also provides a kind of protection. The universe is so large and so empty that destructive forces struggle to reach across the gaps between stars. Planets can orbit their suns in nearly perfect circles, traveling the same path year after year with remarkable consistency. The orbits of most worlds are slightly elongated, but many approach a circular shape so closely that the distance between planet and star remains almost constant throughout the entire journey. This means that seasons on such worlds change very little, and the amount of light and warmth received from the central sun stays nearly the same month after month. Stability becomes the defining feature of these planetary systems. There is something soothing about the regularity of orbital motion. A planet does not need to make decisions or exert effort. It simply follows the path that gravity has carved for it, moving around its star in an endless loop that repeats with extraordinary precision. The same constellations rise and set, the same patterns of light and shadow play across the surface, and the same gentle rhythm governs the passage of time. Millions of years can pass without any significant change to this dance. The planet does not grow tired or lose its way. It simply continues, held in place by invisible forces that never falter. The Milky Way rotates so slowly that a single orbit takes approximately 230 million years. Our Sun, along with all the planets and moons and asteroids that accompany it, travels around the galactic center at a speed that seems impressive by earthly standards, but accomplishes very little on cosmic timescales. Since the Sun formed roughly 4.6 billion years ago, it has completed only about 20 orbits around the galaxy. 20 loops in all that time. The pace is almost unimaginably leisurely. This slow rotation means that the structure of the galaxy changes only gradually. The spiral arms that give our galaxy its distinctive shape are not fixed features, but rather waves of density that drift through the disk of stars over hundreds of millions of years. From one human lifetime to the next, the appearance of the Milky Way remains essentially unchanged. The same band of light stretches across the summer sky, the same dark lanes of dust block portions of that glow, and the same sense of quiet immensity fills anyone who gazes upward on a clear night. Some nebulae stretch across distances so vast that light takes years to travel from one side to the other. These enormous clouds of gas and dust hang in space like silent monuments to the raw materials of creation. Within them, atoms drift and collide with leisurely randomness, occasionally gathering into clumps that will someday become stars. But that process unfolds over millions of years, far too slowly for any observer to witness. For now, the nebulae simply exist, glowing faintly or absorbing the light of more distant stars, remaining essentially unchanged from one century to the next. The colors of nebulae arise from the simplest of causes. Hydrogen atoms, when energized by nearby stars, release a characteristic red glow. Oxygen contributes shades of green and blue. Other elements add their own subtle hues to the mixture, but these colors do not flash or flicker. They persist with the same steady luminosity year after year, century after century. A photograph taken of a nebula today would appear almost identical to one taken 1,000 years from now. The patience of these cosmic clouds is absolute. The coldest places in the universe are found far from any star, in the depths of vast molecular clouds where temperatures approach absolute zero. In these regions, molecular motion slows to a crawl. Atoms barely vibrate. Chemical reactions proceed with extraordinary sluggishness. Time itself seems to hold its breath in these frozen expanses, waiting for something to disturb the profound stillness. And yet nothing disturbs it. The cold persists unchanging for millions of years at a stretch. There is a strange comfort in knowing that such quiet places exist. They represent the ultimate form of rest, a state of near-total inactivity, where nothing happens and nothing is expected to happen. The universe contains countless such regions, scattered between the stars and hiding in the shadows of dense clouds. They ask nothing of the cosmos and contribute nothing except their patient presence. In a universe often described in terms of violence and energy, these cold sanctuaries remind us that stillness is also a fundamental part of existence. Stars, like our Sun, live for approximately 10 billion years, burning through their hydrogen fuel with steady reliability. Our own Sun has reached roughly the halfway point of its life, meaning it will continue shining much as it does today for another 5 billion years. On human time scales, this represents an essentially infinite span of stability. Generations will come and go, civilizations will rise and fall, and still the sun will shine with the same familiar warmth that has greeted every morning since the dawn of life on Earth. This longevity provides a foundation of certainty in an otherwise uncertain universe. Whatever changes occur on the surface of our planet, whatever challenges future generations may face, the sun will continue its quiet work of fusing hydrogen into helium, releasing the energy that makes life possible. The constancy of stellar fusion is one of the most reliable processes in all of nature. It does not falter or skip. It does not require maintenance or intervention. It simply proceeds moment after moment, for spans of time that dwarf every other consideration. The spaces between galaxies contain almost nothing at all. These intergalactic voids stretch for millions of light years, holding perhaps a single atom of hydrogen in every cubic meter of volume. By earthly standards, this represents an emptiness more perfect than any vacuum ever created in a laboratory. And yet, these voids make up most of the volume of the observable universe. Most of existence, in other words, consists of absolutely nothing. This emptiness might seem unsettling, but it can also be understood as a form of cosmic peace. In these vast stretches of nothing, no forces compete, no matter collides, no energy transforms from one state to another. The void simply exists, extending endlessly in all directions, representing pure potential without any current activity. Light from distant galaxies passes through without interruption. Time flows without any events to mark its passage. The intergalactic medium is perhaps the most restful environment imaginable, a realm where nothing whatsoever happens. The moon drifts slowly away from Earth at a rate of approximately 3.8 centimeters per year. This gentle recession has continued for billions of years and will continue for billions more. The process is driven by tidal interactions between our planet and its companion, a gradual transfer of energy that causes the moon to spiral outward at an almost imperceptible pace. In 100 years, the moon will be roughly 4 meters farther away than it is tonight. In 1,000 years, the difference will still be too small to notice with the unaided eye. This slow departure represents one of the gentlest transformations in the solar system. Nothing violent occurs. Nothing breaks or collides. The moon simply drifts outward, maintaining its familiar presence in the night sky while gradually increasing its distance from the world that gave it form. Future generations will still see the same luminous disk rising above the horizon, still watch the same phases wax and wane, still feel the same quiet wonder at the silver light falling across darkened landscapes. The changes happen too slowly to affect any human experience. Jupiter's Great Red Spot has been swirling in the planet's atmosphere for at least 400 years. This enormous storm, large enough to swallow the Earth several times over, rotates with steady persistence, despite all the chaos that must be occurring within its clouds. Winds howl at tremendous speeds, layers of gas rise and fall, and yet the storm as a whole maintains its shape and position decade after decade. It represents a kind of stability born from motion, a system that perpetuates itself through constant activity. There is something almost meditative about a storm that lasts for centuries. On Earth, weather systems come and go within days or weeks. But in the atmospheres of giant planets, the same patterns can persist across time spans that exceed all of recorded human history. The Great Red Spot was there before anyone alive today was born, and it will likely still be there long after everyone alive today has passed. Its endurance suggests that even turbulence can become a form of constancy when viewed from a sufficiently distant perspective. Binary stars orbit each other in graceful dances that repeat with mathematical precision. Two suns bound together by gravity trace ellipses around their common center of mass, never deviating from paths established billions of years ago. Some binaries complete their orbits in days. Others take centuries, but all of them follow trajectories that could be predicted with perfect accuracy if we knew their initial conditions well enough. Chaos has no foothold in these systems. Order prevails across scales of time that exceed comprehension. Watching binary stars through a telescope reveals something about the fundamental nature of the cosmos. Despite all the complexity we observe, the underlying rules are simple and elegant. Gravity pulls objects together in predictable ways. Motion persists unless disrupted by external forces. These principles govern everything from the fall of raindrops to the orbits of galaxies, and they do so without variation or exception. The universe, for all its vastness, operates according to patterns that the human mind can grasp and appreciate. The cosmic microwave background radiation fills all of space with a faint and uniform glow. This ancient light, released when the universe was only 380,000 years old, has been traveling through the expanding cosmos ever since. It has cooled from the incandescent temperatures of the early universe to a frigid 2.7 degrees above absolute zero, becoming invisible to human eyes but detectable by radio telescopes. Every direction you look, this relic radiation streams toward you, a whisper from the earliest epoch of cosmic history. The uniformity of this radiation is remarkable. No matter where you point your instruments, you measure essentially the same temperature, the same faint glow. Tiny variations exist, but they amount to differences of less than 1 part in 100,000. The early universe was almost perfectly smooth, almost perfectly uniform, and that smoothness persists in the radiation that now fills every corner of existence. There is comfort in knowing that the cosmos began in such a state of equilibrium, and that echoes of that balance still surround us on every side. Saturn's rings are composed of countless particles of ice and rock, each one orbiting the planet independently. Despite their individual motions, these particles together create the appearance of solid, stable bands that have circled Saturn for millions of years. Up close, the rings would appear chaotic, with fragments jostling and colliding in complex interactions. But from a distance, all that activity averages out into serene and beautiful structures that seem eternal and unchanging. This emergence of order from underlying chaos offers a metaphor for many aspects of existence. Individual events may seem random and unpredictable, but when viewed from a broader perspective, patterns often emerge. The rings of Saturn demonstrate that stability can arise from billions of independent components, each following its own trajectory, yet collectively producing something coherent and lasting. The cosmos has a way of organizing itself into structures that persist far longer than the individual elements that compose them. Pulsars emit beams of radiation with such regularity that they rival atomic clocks in their precision. These rapidly spinning neutron stars, remnants of massive stars that exploded long ago, sweep their beams across space like cosmic lighthouses. The intervals between pulses can remain stable to within billionths of a second over years of observation. Nothing else in nature produces such consistent timing over such extended periods. This extraordinary regularity arises from the simple physics of rotation. Once set spinning, a neutron star has almost nothing to slow it down. The vacuum of space offers no friction, and the star's compact form resists deformation. So it spins on, pulse after pulse, for millions of years without any detectable change in rhythm. The steadiness of pulsars reminds us that amid all the complexity of the universe, some phenomena achieve a simplicity and constancy that borders on the mathematical. The largest structures in the universe are superclusters of galaxies, interconnected by filaments of dark matter and gas. These cosmic webs span hundreds of millions of light-years, containing billions of galaxies arranged in patterns that resemble soap bubbles or neural networks. The structures grew slowly over billions of years, as gravity gathered matter into progressively larger concentrations. Today, they represent the final stage of large-scale organization in the cosmos. Despite their immense size, superclusters change so slowly that they appear frozen in time from any human perspective. The galaxies within them drift and interact, but the overall structure remains essentially stable across time spans that exceed the age of life on Earth. These vast assemblages of matter demonstrate that even the largest systems can achieve a kind of equilibrium, a balance between gravitational attraction and cosmic expansion that allows them to persist without significant alteration. Some stars are so faint that they barely emit any visible light at all. These dim objects, known as red dwarfs, burn their hydrogen fuel so slowly that they can shine for trillions of years without exhausting their supply. They represent the most common type of star in the galaxy, yet their modest glow makes them invisible to the naked eye, even at relatively close distances. The night sky would look vastly different if our eyes could detect these subtle suns. Red dwarfs embody a philosophy of conservation that contrasts sharply with the profligate burning of more massive stars. They take what they have and make it last, stretching their resources across time spans that the universe itself has not yet experienced. The oldest red dwarfs in the galaxy are still shining much as they did when they first ignited billions of years ago. They will continue shining long after more luminous stars have exhausted their fuel and faded to darkness. The speed of light represents an absolute limit that nothing in the universe can exceed. This cosmic speed limit, roughly 300,000 kilometers per second, governs the flow of information and the spread of influence throughout the cosmos. Nothing can travel faster, which means that events occurring far away cannot affect us immediately. The universe has built-in delays that ensure a kind of cosmic privacy, allowing distant regions to evolve independently without instant interference from elsewhere. This limitation might seem restrictive, but it also provides a form of protection. Dangerous events occurring in distant parts of the galaxy cannot reach us faster than light, which means we always have warning before any threat could arrive. The isolation imposed by the speed of light gives each region of space its own pace and rhythm, free from the instantaneous disruption that would occur in a universe without such constraints. The surface of the Moon has remained essentially unchanged for billions of years, without wind or water to erode its features. The lunar landscape preserves impact craters, and lava flows from the earliest epochs of solar system history. Footprints left by astronauts half a century ago will persist for millions of years, undisturbed by the weathering that would erase them on Earth within days. Time moves differently on the Moon, or rather, its effects accumulate so slowly that they become essentially invisible. This preservation offers a window into the past that no place on Earth can match. The Moon's surface is a museum of cosmic history, displaying features that formed when our planet was still young and violent. Walking on the Moon means walking across terrain that has waited in silence for longer than life has existed on Earth. The patience of that ancient surface is almost beyond comprehension, yet it asks nothing of us except perhaps a moment of quiet appreciation. Galaxies contain vast halos of dark matter that extend far beyond their visible boundaries. These invisible envelopes, composed of particles that neither emit nor absorb light, provide the gravitational scaffolding that holds galaxies together. Without dark matter, the stars we see would fly apart, unable to resist the centrifugal forces of galactic rotation. The visible portions of galaxies represent only a small fraction of their total mass, like foam on the surface of a deep ocean. The presence of dark matter might seem mysterious, but it also represents a form of cosmic support that operates without fanfare or visibility. Dark matter does its work quietly, binding galaxies together without any outward sign of its existence. Only through careful measurement of stellar motions and gravitational effects can we infer its presence. The universe, it seems, contains structures and supports that operate beyond the range of ordinary perception, maintaining order through mechanisms that remain largely hidden. The Andromeda Galaxy is drifting toward the Milky Way at a speed of roughly 110 kilometers per second. Despite this seemingly rapid approach, the two galaxies will not merge for approximately 4 billion years. The distances involved are so vast that even a closure rate of hundreds of kilometers every second amounts to almost no progress on human timescales. For all practical purposes, Andromeda hangs in the same position tonight as it did a century ago, a faint smudge of light visible on clear autumn evenings. When the merger eventually occurs, it will unfold so slowly that any hypothetical observers would barely notice the changes from one generation to the next. Stars will pass each other at comfortable distances, rarely colliding despite the presence of hundreds of billions of them in each galaxy. The event, often described as a collision, would more accurately be called a gradual merging, a gentle intermingling of two vast star systems over hundreds of millions of years. The sun rises and sets according to rhythms established billions of years ago, when the Earth first settled into its current orbit. Every morning's light represents a continuation of patterns that have repeated since before any creatures existed to appreciate them. The angle of sunlight changes with the seasons. The length of days varies with latitude, but all of these variations follow predictable cycles that never fail or surprise. Tomorrow's sunrise will occur at a time that could be calculated with precision years in advance. This reliability forms the foundation of biological life on Earth. Organisms evolved to match their activities to solar rhythms, developing internal clocks that anticipate the rising and setting of the sun. Our own sleep cycles, our feelings of alertness and drowsiness, reflect adaptations to celestial patterns that have remained constant for eons. When you feel sleepy as the night deepens, you are responding to signals that connect you to the fundamental structure of the solar system. Asteroids drift through space in orbits that can remain stable for millions of years. These rocky remnants of the early solar system follow paths established during the era of planetary formation, when the gravitational architecture of the Sun's neighborhood settled into its present configuration. Most asteroids pose no threat to Earth, circling the Sun in the vast region between Mars and Jupiter, where nothing disturbs their lonely journeys. The asteroid belt is far more empty than popular imagination suggests. Spacecraft can pass through it without any significant risk of collision, because the distances between individual asteroids average millions of kilometers. Each rock occupies its own region of space, separated from its nearest neighbors by gulfs of vacuum. The belt represents not a crowded hazard, but a sparsely populated zone where ancient fragments continue their quiet circuits around the Sun. Comets spend most of their existence in the frozen depths of the outer solar system, far from the Sun's warmth. These icy bodies orbit in regions so cold and distant that the Sun appears as little more than a bright star. For thousands of years at a time, a comet may drift through this darkness, experiencing virtually no change, maintaining the same composition it acquired during the earliest stages of solar system formation. Only when gravitational perturbations send it toward the inner solar system does a comet develop the spectacular tail that makes it visible from Earth. Most comets never make that journey. They remain in the distant reaches, undisturbed and unobserved, circling the Sun in orbits that take tens of thousands of years to complete. These unseen wanderers represent a population of objects that may number in the trillions, a vast reservoir of primordial ice that has remained essentially unchanged since the birth of the planets. Their patience exceeds anything we can easily imagine. The electromagnetic spectrum extends far beyond the narrow band of light that human eyes can perceive. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays all represent forms of the same fundamental phenomenon, differing only in their wavelength and energy. The universe is filled with radiation across this entire spectrum, but we experience only a tiny sliver of it directly. Our perception of the cosmos is necessarily incomplete, limited by the biological constraints of our sensory apparatus. This limitation should not trouble us unduly. The portion of the spectrum we can see has been sufficient to guide human activity for millions of years. We evolved eyes sensitive to exactly those wavelengths that prove most useful for navigating our environment during daylight hours. The universe has revealed enough of itself to support the development of intelligent life, and through technology, we have extended our perception into wavelengths our ancestors could never have imagined. Each new window onto the cosmos reveals fresh wonders, yet the fundamental nature of light remains the same across all frequencies. The phases of the moon repeat with a regularity that humans have tracked for tens of thousands of years. From new moon to full moon and back again, the cycle completes itself in approximately 29.5 days, providing one of the most reliable natural timekeepers available to early civilizations. This rhythm arises from the simple geometry of the Earth-Moon-Sun system, as the angle between Sun and Moon changes gradually over the course of each orbit. Nothing about this process is mysterious or unpredictable. It follows from basic principles that anyone can understand. Watching the moon move through its phases offers a gentle lesson in cosmic regularity. The same sequence that unfolded last month will unfold again this month and next month, and for billions of months to come. Slight variations exist, perturbations caused by the gravitational influence of other bodies. But these amount to minor fluctuations around an essentially fixed pattern. The moon's phases have provided comfort and orientation to countless generations, a steady presence in a world that often seems chaotic and unpredictable. The density of interstellar space is so low that a spacecraft traveling through it would encounter almost no resistance. The atoms and molecules scattered between the stars are so widely spaced that collisions with a moving object would be extraordinarily rare. For all practical purposes, interstellar space is empty, a vacuum more perfect than any achievable in laboratories on Earth. Objects moving through this medium can maintain their velocity indefinitely, coasting on trajectories established long ago without any need for additional propulsion. The Voyager spacecraft launched in the 1970s have now entered this interstellar realm, drifting outward from the Sun toward destinations that will take tens of thousands of years to reach. They carry with them records of human civilization, messages intended for recipients who may never exist. Yet even if no one ever finds them, the spacecraft will continue their journeys, traveling through the quiet darkness between stars for longer than human civilization has existed. The gravitational influence of the moon raises tides on Earth, but the effect is so gentle that we barely notice it in daily life. Coastal regions experience the rise and fall of water levels twice each day, but the change amounts to only a few meters even in the most extreme cases. Inland areas feel almost no effect at all. The moon's gravity, though sufficient to move millions of tons of seawater, operates so smoothly and gradually that it never produces sudden or violent changes. These tides have persisted for as long as the moon has orbited the Earth, roughly 4 billion years. Every beach on the planet has experienced this gentle rhythm since the earliest epochs of our world's history. Organisms have adapted to tidal patterns, timing their activities to the regular rise and fall of water. The relationship between Earth and Moon, seemingly distant and abstract, manifests in the daily lives of countless creatures that respond to rhythms established when both worlds were young. Stars form within clouds of gas and dust, but the process unfolds so slowly that no human could watch it happen in real time. From the initial collapse of a dense region to the ignition of nuclear fusion in the core, stellar formation typically requires millions of years. For most of that time, very little seems to be happening. Gas molecules drift together at walking pace, gradually accumulating into ever denser concentrations. Only near the end of the process does the pace accelerate, as gravity pulls the growing protostar together with increasing urgency. This leisurely pace contrasts sharply with human notions of birth and creation. On Earth, new organisms emerge within hours or days, and even the longest pregnancies last less than 2 years. But stars operate on entirely different timescales. A star that began forming before the dinosaurs emerged might only now be reaching the stage of fusion ignition. The cosmos creates its suns with patience that borders on the geological. The constellation patterns visible tonight are essentially the same patterns that ancient Egyptians observed 5,000 years ago. Over such short spans of time, stellar motion produces no detectable change in the arrangement of stars. The Big Dipper looks the same to us as it did to Confucius or Plato or any other figure from recorded history. This stability provides a connection to the past that few other phenomena can match. Of course, over much longer spans. The constellations do change. The stars are all moving relative to one another, drifting through the galaxy at various speeds and in various directions. In 50,000 years, the familiar patterns will have deformed noticeably, and in 1,000,000 years they will have become unrecognizable. But such time spans lie so far beyond human experience that they barely register as relevant. For all practical purposes, the constellations are permanent fixtures of the night sky. The Sun produces energy through nuclear fusion, a process that converts hydrogen into helium deep within the solar core. Approximately 600 million tons of hydrogen undergo this transformation every second, releasing energy equivalent to billions of nuclear weapons. Yet the Sun's output remains remarkably constant from one year to the next. Small variations exist associated with sunspot cycles and other surface phenomena, but the total energy reaching Earth fluctuates by less than a fraction of a percent. This stability arises from the extraordinary balance between gravity and radiation pressure within the Sun. Gravity pulls the solar mass inward, compressing and heating the core. The resulting fusion releases energy that pushes outward against the gravitational collapse. These two forces match each other so precisely that the Sun maintains almost exactly the same size and temperature decade after decade. The equilibrium is self-regulating. If fusion increased, the Sun would expand slightly, cooling the core and reducing the reaction rate. The universe contains roughly 2 trillion galaxies, each one home to hundreds of billions of stars. The scale of this number defies intuitive comprehension. If you could visit a new galaxy every second, it would take you over 60,000 years to see them all. And each galaxy contains more stars than all the grains of sand on all the beaches of Earth. The cosmos is not merely large, it exceeds largeness in ways that language struggles to express. Yet this immensity need not feel overwhelming. Each of those trillions of galaxies exists peacefully in its own region of space, separated from its neighbors by millions of light years. The universe is large enough to accommodate all of them with room to spare. And from your perspective on this particular planet, the vastness of the cosmos appears not as crowding, but as emptiness, a profound solitude that stretches in every direction farther than thought can follow. Many stars spend their lives in binary systems, orbiting a companion sun in patterns that have remained stable for billions of years. These stellar pairs form together from the same cloud of gas and dust, bound by gravity from the earliest moments of their existence. They have circled each other through countless orbits, never colliding, never escaping, simply maintaining the relationship that chance and physics established long ago. Binary stars demonstrate that companionship is a fundamental feature of the cosmos. Solitary objects may seem more common when we look at planets or asteroids, but among stars, binaries are remarkably prevalent. Some estimates suggest that half of all Sun-like stars have at least one stellar companion. The universe, it seems, tends toward connection rather than isolation. Even across the vast distances of space, gravitational bonds can hold objects together for periods that exceed the current age of the cosmos. The observable universe has a radius of approximately 46 billion light-years, representing the greatest distance from which light could have reached us since the Big Bang. Beyond this cosmic horizon, other regions certainly exist, but their light has not yet had time to arrive. We are limited to observing a sphere of finite size, centered on our own location, with boundaries that recede at the speed of light as the universe ages. This limitation applies equally to all observers throughout the cosmos. Every point in space has its own observable universe, its own horizon beyond which nothing can be seen. No observer anywhere has access to complete information about the cosmos. We are all embedded within bubbles of visibility, unable to see past the edges of our own cosmic neighborhoods. This shared limitation connects all potential observers in a strange democracy of ignorance. The chemistry of life depends upon elements forged in the hearts of ancient stars. Carbon, oxygen, nitrogen. and virtually every atom heavier than helium were synthesized through stellar nucleosynthesis and scattered across the galaxy by supernova explosions. The calcium in your bones, the iron in your blood, the oxygen in the air you breathe, all began their existence in the cores of suns that died billions of years ago. We are literally made of star stuff, as the astronomer Carl Sagan famously observed. This origin story connects every living thing to the broader history of the cosmos. The atoms that currently compose your body have existed for billions of years, cycling through stars and clouds and planets before arriving in their present configuration. They will continue existing long after their current arrangement has dispersed, becoming part of other structures and processes that no one can predict. Life represents a temporary gathering of ancient materials, a brief organization of matter that will eventually return to the cosmic pool from which it emerged. Planetary rings are found not only around Saturn, but also around Jupiter, Uranus, and Neptune. Each ring system has its own character, shaped by the specific conditions and history of its host planet. Saturn's rings are bright and broad, composed primarily of ice particles. Jupiter's rings are faint and dusty, barely visible even to spacecraft. Uranus and Neptune possess rings of intermediate properties, dark and narrow but well-defined. The diversity of ring systems demonstrates that multiple pathways can lead to similar cosmic structures. These rings represent materials that never quite managed to form moons. Perhaps they originated from the destruction of existing moons, shattered by impacts, or torn apart by tidal forces. Perhaps they condensed from the primordial disk that surrounded each giant planet during the era of formation. Whatever their origin, they now circle their planets in stable configurations that may persist for millions of years. The rings embody a kind of cosmic patience, materials waiting in orbit for futures that may never arrive. The farthest objects visible to the unaided eye lie approximately 2.5 million light-years away. The Andromeda Galaxy, appearing as a faint smudge of light on clear autumn nights, represents the most distant thing you can see without optical assistance. Every photon striking your retina from that direction began its journey before modern humans evolved, before the ice ages reshaped the continents, before countless species rose and fell on this small planet. The light is ancient beyond ordinary comprehension. Yet that same light continues arriving, moment after moment, a steady stream of photons that links the present to the unimaginably distant past. Andromeda shines tonight just as it shone yesterday, and will shine tomorrow. The connection it provides to cosmic history requires no special equipment or expertise. Anyone who looks in the right direction on a sufficiently dark night can experience directly the tremendous age and size of the universe. The density of stars in the galaxy varies enormously from place to place. Near the galactic center, stars crowd together so closely that the night sky would blaze with brilliance, offering no true darkness at all. In the outer reaches of the galaxy, stars scatter more thinly, and the night reveals vast stretches of emptiness between the points of light. Our own solar system occupies a position roughly 2/3 of the way out from the galactic center, in a region of moderate stellar density that provides dark nights without complete isolation. This location may have influenced the development of life on Earth. A crowded stellar environment might expose planets to dangerous radiation from nearby supernovae or gravitational disturbances from passing stars. An overly sparse environment might deprive young planetary systems of the heavy elements needed for rocky worlds and complex chemistry. The intermediate density of our galactic neighborhood strikes a balance that may favor the emergence and persistence of life. Meteors entering Earth's atmosphere burn up harmlessly in brilliant streaks of light. These fragments of cosmic debris, usually no larger than grains of sand, encounter air molecules at such high speeds that friction heats them to incandescence. For a brief moment, they glow brighter than any star, tracing paths across the sky that vanish almost as quickly as they appear. Then they are gone, their material dispersed into the upper atmosphere as fine dust that slowly settles toward the ground. On any clear night, patient observers can expect to see several meteors per HR. During meteor showers, when Earth passes through streams of debris left by comets, the rate can increase to dozens or even hundreds per HR. These displays have inspired wonder and curiosity throughout human history, providing natural fireworks that require no human intervention. The cosmos puts on its own shows, asking nothing in return except perhaps a willingness to look upward. The gravitational attraction between distant galaxies operates across spans of millions of light years. Despite the unimaginable distances involved, gravity reaches out with patient persistence, pulling on mass regardless of how far away it may be. Superclusters of galaxies hold together through these long-range attractions, maintaining their structures across distances that light requires millions of years to traverse. The universe is connected by invisible threads of gravitational influence that link even the most widely separated objects. This connectivity provides a form of cosmic unity that contrasts with the apparent isolation of individual objects. Every mass attracts every other mass, no matter how slight the force or how great the separation. The Earth tugs on distant quasars, and distant quasars tug on Earth, though the effects are far too small to measure. In principle, the entire universe forms a single gravitationally bound system, with every part influencing every other part across the full extent of space and time. The night sky changes slowly through the seasons, as Earth's orbit carries us around the Sun and shifts our perspective on the surrounding stars. Constellations that dominate the winter sky sink below the horizon in summer, replaced by different patterns that have their own character and mythology. This annual cycle has repeated unchanged for as long as humans have looked upward, providing a natural calendar that predates all artificial timekeeping systems. The reliability of seasonal changes in the sky offered early civilizations their first insights into cosmic regularity. Long before anyone understood the mechanics of planetary motion, people recognized that certain stars rose and set at predictable times each year. This knowledge allowed them to anticipate seasonal changes on Earth, planning agricultural activities in harmony with celestial rhythms. The sky became a vast clock, marking the passage of time with stars instead of hands. The composition of distant stars can be determined by analyzing the light they emit. Each element absorbs and emits light at characteristic wavelengths, creating spectral fingerprints that reveal what materials are present and in what quantities. Through spectroscopy, astronomers can determine the chemical makeup of objects that no human will ever visit, translating starlight into detailed inventories of elemental abundances. This technique has revealed that stars throughout the observable universe are composed of the same elements found on Earth. Hydrogen and helium dominate everywhere, just as they do in our Sun. Heavier elements appear in proportions that vary with the age and history of each star. But the same basic periodic table applies from one end of the cosmos to the other. The chemistry of the universe is universal in the most literal sense. The rotation of the Earth produces the apparent motion of stars across the night sky. As our planet spins on its axis, different portions of the celestial sphere come into view and then slip below the horizon. Stars appear to rise in the east and set in the west, tracing arcs across the sky that reflect not their own movement, but ours. This same rotation produces the cycle of day and night, the alternation between illumination and darkness that governs the rhythms of life on Earth. Standing still on the Earth's surface, you are actually moving through space at a speed of roughly 1,600 kilometers per h/hour at the equator. Yet this motion produces no sensation of velocity, no wind or vibration, or any other cue that you are hurtling through space. The rotation is so smooth and constant that it becomes invisible through familiarity. Only by watching the stars drift slowly across the sky can you perceive the motion that carries you around the axis of the world. Many exoplanets orbit within the habitable zones of their host stars, where temperatures could allow liquid water to exist on their surfaces. These planets occupy a range of distances that provides neither too much heat nor too little, creating conditions that might support the kind of chemistry that underlies life on Earth. The discovery of such planets has expanded our understanding of where life might emerge and how common habitable environments may be throughout the galaxy. None of these distant worlds has yet yielded evidence of life, and detecting such evidence remains beyond current technological capabilities. But the existence of so many potentially habitable planets suggests that the conditions for life are not particularly rare. If life has emerged on Earth, it may well have emerged elsewhere under similar circumstances. The universe contains countless experiments in habitability, running simultaneously across billions of years and trillions of worlds. The vacuum of space is not truly empty, but contains fields that permeate all of existence. Electromagnetic fields, gravitational fields, and more exotic quantum fields fill every point in the cosmos, shaping the behavior of matter and energy at every scale. Even in the deepest void between galaxies, these fields persist, providing the substrate upon which physical phenomena unfold. What appears to be emptiness is actually structured by invisible influences that govern the nature of reality. These fields represent the fundamental architecture of the universe, the framework within which particles move and forces operate. Without them, matter could not exist, light could not propagate, and the cosmos would be utterly different from the one we inhabit. The apparent void of space is actually dense with physical significance, a medium through which the basic processes of nature continuously unfold. The age of the universe, approximately 13.8 billion years, represents the span of time since the Big Bang initiated cosmic expansion. This duration exceeds human comprehension by orders of magnitude. If the entire history of the universe were compressed into a single year, human civilization would occupy only the final few seconds of the 31st of December. Our species has witnessed an almost infinitesimal fraction of cosmic history, arriving recently in a universe that had been developing for billions of years before our emergence. This perspective can foster humility rather than insignificance. We are latecomers to a cosmos that prepared itself for our arrival through eons of stellar nucleosynthesis and planetary formation. The elements that compose our bodies, the conditions that permit our existence, all of these required billions of years of cosmic evolution to produce. We are the current result of processes that began long before any planet existed to harbor life. The sun's light takes approximately 8 minutes to reach Earth after leaving the solar surface. This means that when you look at the sun, you see it not as it is, but as it was 8 minutes ago. If the sun were to suddenly vanish, we would continue receiving its light for another 8 minutes, unaware that our star had disappeared. This delay illustrates the finite speed of light and the corresponding delay in information transfer across cosmic distances. Such delays become far more significant when dealing with more distant objects. The light from Proxima Centauri, the nearest star beyond the Sun, requires over 4 years to reach us. Light from the center of our galaxy takes roughly 26,000 years. Light from distant galaxies may have traveled for billions of years before arriving at Earth. Astronomy is necessarily a study of the past, with more distant objects revealing ever more ancient states of the universe. Globular clusters contain some of the oldest stars in the galaxy, objects that formed when the Milky Way itself was young. These dense spherical collections of stars orbit the galactic center like ancient satellites, preserving stellar populations that date back nearly to the beginning of the universe. The stars within globular clusters are typically old and cool, having exhausted most of their hydrogen fuel over billions of years of steady burning. Studying globular clusters offers insight into conditions that prevailed when the galaxy was forming. The chemical compositions of their stars reflect the limited supply of heavy elements available in the early cosmos, before generations of supernovae had enriched the interstellar medium. These ancient assemblages serve as time capsules, preserving information about epochs that no other type of object can reveal. The auroras that dance across polar skies result from interactions between solar wind particles and Earth's magnetic field. Charged particles streaming from the Sun encounter our planet's magnetic defenses and spiral down toward the poles, where they collide with atmospheric molecules and cause them to emit light. The resulting displays can fill vast portions of the sky with shimmering curtains of green, red, purple, and blue. These lights represent a visual manifestation of the invisible shield that protects our planet from the harsh environment of space. Without Earth's magnetic field, the solar wind would strip away our atmosphere over millions of years, transforming our world into a barren rock like Mars. The auroras testify to the ongoing battle between our planet's defenses and the relentless stream of particles ejected by the Sun. The deep field images captured by space telescopes reveal thousands of galaxies in patches of sky that appear empty to the naked eye. These observations demonstrate that even the most apparently vacant regions of space contain vast populations of distant galaxies, each one a universe of stars unto itself. The cosmos is filled with structures beyond counting, extending in every direction as far as instruments can see. Such images convey the sheer abundance of the universe more powerfully than any numerical description. Where the unaided eye sees only darkness, telescopes reveal layer upon layer of luminous structures, distributed through space without apparent limit. The emptiness of the night sky is an illusion created by the limitations of human vision. In reality, the cosmos teems with galaxies that have been shining for billions of years, waiting only for instruments sensitive enough to detect their ancient light. Now let your thoughts begin to drift like distant starlight, traveling through the silent void. The facts you have heard tonight require nothing further from you. They simply are, like the stars themselves, existing whether anyone contemplates them or not. The universe continues its patient expansion, its slow rotation, its steady shining, without any need for your attention or effort. Feel your breathing, slow to match the unhurried rhythms of the cosmos. There is no destination you must reach, no task you must complete before the morning. The night welcomes you just as space welcomes the countless objects that drift through its depths. You can let go of the day's concerns as easily as a comet releases its tail when it moves away from the sun. The pillow beneath your head supports you with the same reliable constancy that gravity provides throughout the universe. The darkness around you resembles the darkness between stars, peaceful and undisturbed. You are safe here, held in place by forces that have governed matter since the beginning of time. If you are still awake, allow the remaining facts to carry you closer to sleep. Each one requires less attention than the last. Each one invites you to release a little more of your grip on wakefulness. The cosmos will still be there when you wake, unchanged and unchanging on any time scale that matters to human experience. The gentle hum of cosmic radiation fills every corner of the universe with a whisper so faint that only the most sensitive instruments can detect it. This background noise represents the accumulated glow of countless processes unfolding across billions of years. It surrounds you now, passing through walls and bodies without interaction, a constant presence that asks nothing and disturbs nothing. The universe murmurs continuously, but its voice is so soft that silence seems absolute. Consider how this radiation began its journey from sources scattered across the observable cosmos. Some photons originated in the hearts of distant galaxies, where matter spirals toward enormous concentrations of gravity. Others emerge from the surfaces of ordinary stars, released during the steady fusion reactions that power stellar luminosity. Still others trace their origins to the earliest epochs of cosmic history, when the universe was dense and hot and filled with a brilliant glow that has since cooled to near invisibility. The orbital periods of planets follow mathematical relationships that Johannes Kepler discovered over 4 centuries ago. A planet twice as far from its star does not simply take twice as long to complete an orbit. The relationship is more complex, involving the 3/2 power of distance. Yet despite this mathematical complexity, the underlying principle is elegantly simple. Gravity and orbital motion obey precise laws that apply everywhere in the cosmos, without exception. These laws mean that planetary motion is perfectly predictable over spans of time that exceed anything humans can directly experience. We can calculate exactly where Mars will be 1,000 years from now, or where it was 1,000 years ago. The planets do not wander randomly, but follow trajectories determined by their initial conditions and the gravitational influences they experience. This predictability transforms the night sky from a realm of mystery into a cosmic clockwork, regular and reliable beyond human capability to match. Distant quasars shine with the luminosity of hundreds of ordinary galaxies combined, yet they occupy regions of space smaller than our solar system. These brilliant beacons mark the locations of supermassive black holes actively consuming surrounding matter. As gas spirals inward, it heats to temperatures that produce light across the entire electromagnetic spectrum. The result is a point of brilliance visible across billions of light years, a lighthouse that has guided astronomers toward understanding the nature of the early universe. Despite their violent origins, quasars represent processes that unfold with surprising steadiness. The accretion of matter onto a black hole can continue for millions of years, maintaining a relatively constant luminosity throughout that period. The apparent brightness of a quasar may fluctuate on shorter timescales, reflecting variations in the flow of material toward the central object. But these fluctuations occur around a mean value that persists far longer than any human lifetime. Even the most energetic phenomena in the cosmos can achieve a kind of dynamic equilibrium. The colors of stars reveal their surface temperatures through a relationship so consistent that astronomers can estimate stellar heat simply by observing the color of their light. Blue stars burn hotter than white stars, which burn hotter than yellow stars like our sun. Orange and red stars are cooler still, their surfaces radiating at temperatures that would freeze many familiar substances on Earth. This color-temperature relationship applies to every star in the visible universe, a universal law that connects distant suns to the physics we understand on our own world. When you look at the night sky, you observe this relationship directly. The brightest stars display a range of colors that reflects the diversity of stellar temperatures throughout the galaxy. Some shine with a bluish tint, indicating surfaces hot enough to ionize most materials. Others glow with the familiar yellow of our sun, or the orange and red hues of cooler stellar photospheres. Each color tells a story of nuclear processes occurring deep within the stellar core, translated into visible light that travels across the void to reach your eyes. The cosmic distance ladder allows astronomers to measure the separation between objects across the entire observable universe. This ladder consists of multiple techniques, each building upon the last, extending our reach from nearby stars to the most distant galaxies. At the base of the ladder, parallax measurements determine the distances to stars within a few hundred light-years by observing how their apparent positions shift as Earth moves around the Sun. This geometric method requires no assumptions about stellar properties and provides the most reliable distance estimates available, beyond the range of parallax. Astronomers employ standard candles, objects whose intrinsic brightness can be determined through independent means. By comparing the apparent brightness of such objects to their known luminosity, the distance can be calculated through simple geometry. Cepheid variable stars served as crucial standard candles for much of the 20th century, their pulsation periods revealing their intrinsic brightness with remarkable precision. Type ER supernovae extend the ladder to cosmological distances, their explosions producing consistent peak luminosities that can be observed across billions of light-years. The chemical elements, heavier than iron, form, primarily through processes even more violent than ordinary stellar fusion. When massive stars explode as supernovae, the intense conditions create elements that cannot be produced through the slower reactions occurring in stellar cores. Neutron star mergers generate additional heavy elements through rapid neutron capture, building atomic nuclei far heavier than anything that could form in normal stellar environments. Gold, platinum, uranium, and many other heavy elements owe their existence to these cataclysmic events. Yet, despite their violent origins, these elements now compose familiar objects throughout the world around you. The gold in jewelry, the lead in batteries, the uranium in nuclear fuel, all began in environments of unimaginable violence. The cosmos recycles its materials with remarkable efficiency, transforming the debris of stellar explosions into the building blocks of planets, oceans, and living organisms. The history of violence becomes a foundation for stability, as elements forged in catastrophe settle into peaceful configurations that persist for billions of years. The rotation of galaxies reveals the presence of matter invisible to telescopes. When astronomers measure the speeds at which stars orbit galactic centers, they find velocities that exceed what the visible mass could produce. The outer regions of galaxies rotate too quickly, as if additional matter were present beyond what can be seen. This discrepancy led to the hypothesis of dark matter, an invisible substance that interacts gravitationally, but neither emits nor absorbs electromagnetic radiation. Dark matter appears to outweigh ordinary matter, by a factor of roughly 5 to 1 throughout the universe. Most of the mass in galaxies consists of this invisible component, with visible stars, gas, and dust representing only a small fraction of the total. The universe is dominated by substances that remain hidden from direct observation, revealing themselves only through their gravitational effects on visible structures. This realization has fundamentally altered our understanding of cosmic composition, demonstrating that the visible cosmos represents only a small portion of what actually exists. Planetary atmospheres come in an extraordinary variety of compositions, from the nitrogen-oxygen mixture we breathe on Earth to the hydrogen-helium envelopes of giant planets. Some atmospheres contain exotic chemicals that would poison any terrestrial organism, while others approach conditions that might support familiar forms of life. The diversity of atmospheric chemistry reflects the range of conditions under which planets form and evolve, shaped by distance from their stars, internal heat, volcanic activity, and countless other factors. Venus possesses an atmosphere so thick that its surface pressure exceeds Earth's by a factor of 90. Carbon dioxide dominates this crushing envelope, trapping solar heat through an extreme greenhouse effect that raises surface temperatures above the melting point of lead. Mars, by contrast, has lost most of its original atmosphere to space, leaving a thin layer of carbon dioxide that provides almost no protection from radiation or temperature extremes. Each planet tells a story through its atmosphere, revealing processes that shaped its development over billions of years. The gravitational waves predicted by Einstein's general relativity travel through space at the speed of light, carrying information about the most violent events in the cosmos. When massive objects accelerate, they disturb the fabric of space-time, producing ripples that propagate outward in all directions. These waves stretch and compress space itself as they pass, though the effects are so subtle that they remained undetectable for a century after their theoretical prediction. Modern gravitational wave observatories have finally achieved the sensitivity needed to detect these cosmic ripples. The first confirmed detection came in 2015, when instruments in Louisiana and Washington state registered the characteristic signal of two black holes merging over 1 billion light-years away. Since then, dozens of additional detections have opened a new window onto the universe, revealing events that produce no electromagnetic radiation visible to conventional telescopes. The cosmos now speaks to us through multiple channels, each carrying unique information about processes occurring throughout the observable universe. The magnetic fields of planets arise from the motion of conductive fluids deep within their interiors. Earth's magnetic field originates in the liquid iron outer core, where convection currents generate electrical currents that produce magnetic effects. This dynamo process requires specific conditions: a fluid conductive enough to carry current, motion vigorous enough to sustain the generating process, and rotation sufficient to organize the resulting field. Planets lacking these conditions possess no global magnetic field. Earth's magnetic field provides crucial protection from the solar wind, deflecting charged particles that would otherwise strip away our atmosphere over geological timescales. The field extends thousands of kilometers into space, creating a magnetic bubble around our planet that shields the surface from harsh radiation. Without this protection, life as we know it could not have developed. The invisible shield above our heads represents one of the fortunate circumstances that distinguish our world from less hospitable planets. The light curves of eclipsing binary stars reveal the properties of objects too distant to observe directly. When one star passes in front of another, as seen from Earth, the combined light from the system drops by an amount that depends on the relative sizes of the two stars. By analyzing these periodic dips in brightness, astronomers can determine the diameters, masses, and temperatures of stars that appear as single points of light even through the largest telescopes. This technique has proven especially valuable for studying exoplanets, which produce similar dips when they transit across the faces of their host stars. The depth of the transit reveals the planet's size relative to its star, while the timing of successive transits reveals the orbital period. Careful analysis of transit light curves has detected thousands of exoplanets, including many that approach the size of Earth. The cosmos reveals its secrets through subtle variations in brightness that patient observation can detect and interpret. The zones of habitability around stars vary in size according to stellar luminosity. Brighter stars produce larger habitable zones, with planets able to maintain liquid water at greater distances. Dimmer stars possess smaller habitable zones, requiring planets to orbit much closer to receive sufficient warmth. These geometric considerations shape the search for potentially habitable exoplanets, focusing attention on worlds that occupy the temperature ranges consistent with liquid water. Red dwarf stars, the most common type of star in the galaxy, present unique challenges for habitability. Their habitable zones lie so close to the stellar surface that planets within them may become tidally locked, with one hemisphere perpetually facing the star while the other remains in darkness. Such worlds would experience extreme temperature contrasts between their light and dark sides, with narrow twilight zones potentially offering more moderate conditions. Whether life could emerge under such circumstances remains an open question. The interstellar medium contains a mixture of gas and dust that permeates the space between stars. This material represents the raw ingredients from which new stars and planets form, recycled through countless generations of stellar birth and death. Most of the gas consists of hydrogen, the simplest and most abundant element in the universe. Dust grains, though far less massive, absorb and scatter starlight in ways that profoundly affect astronomical observations. Regions of space where the interstellar medium is particularly dense appear as dark nebulae, blocking the light of more distant stars. These cold, dense clouds represent the birthplaces of new stellar systems, where gravity can overcome the thermal motion of gas molecules and initiate collapse. The dust within these clouds plays a crucial role in the process, radiating away heat that would otherwise prevent the gas from contracting. Star formation depends on a delicate balance between gravitational attraction and thermal pressure, mediated by the properties of interstellar dust. The proper motions of stars can be detected through careful measurements, taken years or decades apart. As stars move through the galaxy, their positions on the sky change very slightly over time. These changes are so small that only precise astrometric observations can detect them, but accumulated over centuries, they would eventually alter the familiar shapes of constellations. The stars are not fixed, but in constant motion, drifting through space on trajectories that have carried them from distant origins to their current positions. Barnard's star, located about 6 light-years from the Sun, possesses the largest proper motion of any star visible from Earth. It moves across the sky at a rate that would carry it the apparent diameter of the full moon in just 180 years. Most stars move far more slowly, their proper motions requiring thousands of years to produce noticeable changes in position. But all stars share this fundamental property of motion through space, their apparent stillness, an illusion created by the vast distances involved. The stellar populations of galaxies vary in age and composition, according to their locations. Near galactic centers, older stars predominate, their orange and red colors reflecting billions of years of cooling since formation. In spiral arms, younger stars shine with bluer light, having formed recently from gas enriched by previous generations of stellar evolution. This spatial variation in stellar age tells the story of galactic development, revealing how star formation has progressed differently in different regions over cosmic time. Elliptical galaxies typically contain older stellar populations than spiral galaxies, suggesting that their star formation peaked early and has since declined. Spiral galaxies continue forming stars at modest rates, their disks replenished by gas that falls inward from surrounding halos. Irregular galaxies often show vigorous star formation triggered by interactions with larger neighbors. The diversity of galactic forms reflects the diversity of formation histories, each galaxy carrying the record of its development in the properties of its stellar populations. The nucleosynthesis occurring in stellar cores follows sequences determined by temperature and density. Hydrogen fusion, the simplest nuclear reaction, powers most stars throughout the majority of their lifetimes. As hydrogen in the core depletes, helium accumulates until conditions allow helium fusion to begin, producing carbon and oxygen. More massive stars continue through additional stages, fusing progressively heavier elements until iron accumulates in the core and no further energy-releasing reactions are possible. Each stage of nucleosynthesis requires higher temperatures than the last, achieved through the gravitational contraction that occurs when the previous fuel source exhausts. The Sun will eventually reach the helium-burning stage, expanding into a red giant before settling into a final cooling phase. More massive stars progress through the complete sequence, building up iron cores that eventually collapse under their own weight. The elements created through these processes represent the cosmic legacy of stars, scattered through space to become the materials from which future worlds are built. The tidal locking of moons to their planets results from the same gravitational interactions that raise ocean tides on Earth. When a smaller body orbits a larger one, tidal bulges form in response to the gravitational gradient across the smaller body. If the smaller body rotates faster than it orbits, friction within these bulges gradually slows its rotation until it matches the orbital period. At this point, the same hemisphere always faces the planet, and the bulges remain stationary relative to the underlying surface. Our moon achieved tidal locking early in its history, which is why we always see the same face from Earth. Many moons throughout the solar system share this property, their rotation periods matching their orbital periods with remarkable precision. The process requires millions or billions of years to complete, but once achieved, it represents a stable configuration that can persist indefinitely. Tidal locking demonstrates how gravitational interactions can permanently alter the rotation of celestial bodies. The temperature of empty space far from any star approaches absolute zero, but never quite reaches it. The cosmic microwave background radiation provides a floor of approximately 2.7 Kelvin, the residual warmth from the Big Bang that permeates all of space. This temperature represents the coldest possible environment in the natural universe, a deep freeze that has persisted for billions of years and will continue essentially unchanged for billions more. At such temperatures, most chemical processes halt completely. Atoms barely vibrate, molecules cannot undergo the collisions needed for reactions, and matter enters states governed by quantum mechanics rather than classical physics. The cold of deep space represents the ultimate limit of thermal inactivity, a baseline from which any addition of heat produces dramatic effects. Yet even this extreme cold is not absolute zero, that mathematical ideal remaining forever unreachable in any real physical system. The light from distant supernovae reveals the accelerating expansion of the universe. When astronomers compare the apparent brightness of Type Ia supernovae to their known intrinsic luminosity, they can calculate the distance to these stellar explosions. Plotting these distances against the redshifts of their host galaxies reveals a relationship that implies the universe is not merely expanding but expanding at an increasing rate. Something is pushing the cosmos apart with growing urgency. This discovery, made in the late 1990s, introduced the concept of dark energy into cosmology. Whatever causes the accelerating expansion remains mysterious, but its effects dominate the large-scale evolution of the universe. Dark energy appears to comprise roughly 68% of the total energy content of the cosmos, dwarfing both dark matter and ordinary matter. The fate of the universe will be determined by the properties of this enigmatic component, which continues pushing galaxies apart at ever-increasing speeds. The shapes of galaxies fall into several broad categories that reflect their formation histories and current states. Spiral galaxies like our Milky Way possess flattened disks with prominent spiral arms, supported by the rotation of their stellar populations. Elliptical galaxies appear as smooth, rounded systems without disk structure, their stars orbiting in random orientations rather than organized rotational motion. Irregular galaxies lack the symmetry of either spirals or ellipticals, often showing signs of gravitational disturbance from interactions with neighbors. The morphology of a galaxy correlates with other properties such as stellar age, gas content, and ongoing star formation. Spiral galaxies tend to contain more gas and younger stars than ellipticals, which are dominated by old stellar populations and show little current star formation. These correlations suggest that galaxy morphology develops through processes that also affect the broader history of stellar activity within each system. The orbital resonances between moons and planets can maintain stable configurations for billions of years. When the orbital period of one body forms a simple ratio with that of another, the repeated gravitational interactions at the same orbital phases can reinforce particular arrangements rather than disrupting them. Jupiter's inner moons demonstrate this principle, with Io, Europa, and Ganymede locked in a 1:2:4 resonance that has persisted since the early solar system. These resonances can produce dramatic effects on the bodies involved. The continuous gravitational pumping that Io experiences from its resonance with Europa generates intense tidal heating, driving the volcanic activity that makes Io the most geologically active body in the solar system. Europa's resonance generates enough heat to maintain a liquid water ocean beneath its icy surface. Orbital dynamics thus connect to geology through the medium of tidal energy, demonstrating how gravitational relationships shape the internal evolution of worlds. The half-lives of radioactive elements provide natural clocks that allow dating of rocks, fossils, and cosmic samples. Each radioactive isotope decays at a characteristic rate, unaffected by temperature, pressure, or chemical environment. By measuring the ratio of parent isotopes to daughter products, scientists can determine how long the decay process has been occurring, yielding ages that span from recent decades to billions of years. Uranium-lead dating has established the age of Earth at approximately 4.5 billion years, a figure confirmed by multiple independent methods. Meteorites show similar ages, indicating that the entire solar system formed within a relatively brief interval. The consistency of these measurements across different samples and different techniques provides strong confidence in the resulting age estimates. Radioactive decay offers a cosmic stopwatch that records the passage of time with unwavering precision. The composition of planetary atmospheres can change dramatically over geological timescales. Earth's atmosphere has transformed from an oxygen-free mixture dominated by carbon dioxide and nitrogen to the oxygen-rich envelope we breathe today. This transformation resulted primarily from biological activity, as photosynthetic organisms released oxygen that gradually accumulated over hundreds of millions of years. The atmosphere we depend upon for survival is itself a product of life. Mars and Venus may have possessed more hospitable atmospheres in the distant past. Evidence suggests that Mars once had liquid water on its surface, implying a thicker atmosphere, capable of sustaining warmer temperatures. Venus may have been cooler before a runaway greenhouse effect transformed its climate. The current states of these planets represent the endpoints of evolutionary processes that unfolded over billions of years, with Earth representing a different pathway through the space of possible outcomes. The luminosity of stars spans an enormous range, from red dwarfs thousands of times dimmer than the Sun to blue supergiants, hundreds of thousands of times brighter. This range reflects the steep dependence of stellar luminosity on mass, with more massive stars burning their fuel at vastly higher rates. A star twice as massive as the Sun shines roughly 10 times brighter, while a star 10 times as massive shines 10,000 times brighter. These relationships emerge from the physics of stellar structure, where higher mass produces higher core temperatures and more vigorous nuclear burning. The consequences of this luminosity-mass relationship include dramatic differences in stellar lifetimes. High-mass stars exhaust their fuel in mere millions of years, while low-mass stars can shine for trillions of years on the same hydrogen supply. The Sun's 10 billion-year lifespan represents a middle ground, long enough for complex life to evolve on orbiting planets, yet short enough that we can observe the entire sequence of stellar evolution playing out in different stars throughout the galaxy. The volcanic activity of rocky worlds reflects their internal heat budgets and geological histories. Earth remains geologically active because radioactive decay in its interior generates sufficient heat to drive mantle convection and plate tectonics. Mars, smaller and therefore cooling faster, has largely lost its internal heat and shows no current volcanic activity. Venus appears geologically active, but lacks plate tectonics, its surface shaped by volcanic processes operating under a regime different from Earth's. Io, one of Jupiter's moons, demonstrates that internal heat can arise from sources other than radioactivity. Tidal heating driven by Io's orbital resonance with other moons produces more heat per unit area than any other body in the solar system. Volcanoes on Io erupt continuously, resurfacing the moon so rapidly that impact craters cannot accumulate. The cosmic palette of volcanic activity extends from worlds where volcanism has long since ceased to worlds where it continues at rates that dwarf anything on Earth. The gravitational influence of giant planets shaped the structure of our solar system during its early history. Jupiter and Saturn, forming first from the primordial disk, created perturbations that swept material into certain regions while clearing it from others. The asteroid belt between Mars and Jupiter represents material that could never accumulate into a planet due to Jupiter's disruptive influence. The Kuiper belt beyond Neptune was similarly shaped by gravitational interactions with the outer planets. This gravitational sculpting may have influenced the development of life on Earth by determining the rate of impacts from asteroids and comets. A solar system without giant planets might experience more frequent catastrophic collisions, while one with differently positioned giants might experience fewer. The particular arrangement of our planetary system may represent one of many factors that contributed to Earth's habitability, though the relative importance of this factor remains a subject of ongoing research. The cosmic abundance of elements follows a pattern established by stellar nucleosynthesis. Hydrogen and helium, formed primarily in the Big Bang, comprise approximately 98% of ordinary matter by mass. Heavier elements become progressively less abundant, with peaks at iron and nickel representing the endpoints of fusion in massive stellar cores. Elements beyond iron show a gradual decline punctuated by peaks at specific isotopes produced efficiently in particular nucleosynthetic processes. This cosmic abundance pattern is reflected in the composition of the Sun, Earth, and indeed all matter throughout the observable universe. The relative scarcity of heavy elements explains why gold is precious and iron is common, why carbon-based life could develop while more exotic chemistries remained unrealized. The universe dealt the cards that determined what chemistry was possible, and those cards were shuffled in stellar cores billions of years ago. The night sky visible from Earth contains roughly 6,000 stars bright enough to see with the unaided eye under ideal conditions. This number, while impressive, represents only a tiny fraction of the roughly 100 billion stars in our galaxy, which itself represents only one of roughly 2 trillion galaxies in the observable universe. The visible stars are those closest to us and brightest in intrinsic luminosity, a biased sample that tells only part of the cosmic story. Most of the stars in the galaxy are red dwarfs too dim to see from Earth without telescopes. These modest suns far outnumber their brighter cousins, populating the galaxy with countless pinpoints of light invisible to human eyes. If we could see in infrared, the night sky would appear far more crowded, filled with the gentle glow of cool stellar surfaces that emit most of their light at wavelengths our eyes cannot detect. The atmospheres of giant planets extend continuously from their visible cloud tops to their dense interiors. Unlike terrestrial planets, which have clear boundaries between atmosphere and surface, giant planets possess no solid ground. Descending into their atmospheres, one would encounter progressively denser gas that transitions smoothly into liquid and eventually into exotic high-pressure states, with properties unlike any common material. There is no surface to land on, only endless layers of gas and fluid. Jupiter's atmosphere demonstrates this continuous gradation, with its famous cloud bands representing only the outermost layers of a much deeper structure. Beneath the visible clouds lies a vast ocean of liquid hydrogen, compressed by the weight of the overlying atmosphere to densities comparable to water. Deeper still, the pressure becomes so extreme that hydrogen takes on metallic properties, conducting electricity and generating the magnetic field that surrounds the planet. The boundary between atmosphere and interior is a matter of definition rather than physical reality. The precession of Earth's axis traces a slow circle in the sky over approximately 26,000 years. This wobble, caused by the gravitational influence of the Sun and Moon on Earth's equatorial bulge, gradually shifts the direction that Earth's axis points relative to the stars. Currently, the axis points toward Polaris, making it our North Star. Thousands of years ago, different stars served this purpose, and thousands of years hence, still different stars will take the role. This precession affects the timing of seasons relative to Earth's orbital position. The points where Earth reaches its closest and farthest distances from the Sun gradually shift through the calendar year, altering the intensity of seasonal contrasts over cycles that span tens of thousands of years. These orbital variations have been implicated in the timing of ice ages, demonstrating how subtle celestial mechanics can influence climate on geological timescales. The detection of exoplanets through radial velocity measurements exploits the slight wobble that orbiting planets induce in their host stars. As a planet orbits, its gravitational pull causes the star to move in a small circle or ellipse around the system's center of mass. This motion produces periodic shifts in the wavelength of starlight, with the star appearing slightly bluer when moving toward us and slightly redder when moving away. Precise spectrographs can detect these shifts and reveal the presence of planets too distant to observe directly. This technique proved crucial in the early days of exoplanet discovery, revealing the first planets beyond our solar system in the 1990s. The magnitude of the radial velocity wobble depends on planetary mass and orbital distance, with massive planets in close orbits producing the largest signals. Initial discoveries therefore favored these hot Jupiters, though improved instrumentation has since enabled detection of smaller planets at greater distances from their stars. The escape velocity from a celestial body determines what objects can leave its gravitational influence. For Earth, this velocity is approximately 11.2 kilometers per second, fast enough that an object traveling at this speed will never fall back regardless of the direction it travels. Smaller bodies like the Moon have lower escape velocities, making it easier for objects to leave their surfaces. Giant planets have higher escape velocities, their stronger gravity requiring greater speeds to overcome. This concept explains why Earth retains a substantial atmosphere, while the Moon has essentially none. Gas molecules at the top of an atmosphere constantly move at speeds determined by temperature. On the Moon, even relatively slow molecules can exceed the escape velocity and drift away into space. On Earth, only the fastest molecules in the upper atmosphere reach escape velocity. So the atmosphere persists. Atmospheric retention thus depends on a balance between temperature and gravitational strength. The metallicity of stars reflects the enrichment of the galaxy over cosmic time. Astronomers use the term metal to refer to any element heavier than helium, regardless of whether it behaves as a metal in the chemical sense. Stars formed from primordial gas contain almost no metals, while stars formed more recently incorporate the products of previous stellar generations. Measuring stellar metallicity therefore provides information about when and where a star formed. The Sun's metallicity is higher than average for stars of its age, suggesting formation from material that had been processed through multiple stellar generations. Stars in the galactic halo typically show very low metallicity, reflecting their formation in the early universe before much enrichment had occurred. The most metal-rich stars are found in regions with extensive star formation histories, where many generations of stars have lived and died, each contributing its nucleosynthetic products to the interstellar medium. The rotation rates of stars can be measured through their effects on spectral line widths. A rotating star presents different parts of its surface at different velocities relative to the observer, with one limb approaching while the other recedes. The resulting Doppler shifts broaden the absorption lines in the star's spectrum, with faster rotation producing broader lines. This technique has revealed that young stars typically rotate more rapidly than old ones, their rotation gradually slowing over time. Stellar rotation affects many aspects of stellar behavior, from the generation of magnetic fields to the loss of angular momentum through stellar winds. Rapidly rotating stars develop stronger magnetic fields than slowly rotating ones, which in turn produce more intense stellar activity, including flares and coronal mass ejections. As stars age and slow their rotation, their magnetic activity declines, and they settle into quieter phases. The Sun has reached this quieter stage, its rotation having slowed considerably since its youth. The curvature of space-time around massive objects produces effects that have been confirmed through multiple observations. Light passing near massive objects bends slightly, following the curved geometry of space-time, rather than straight lines through flat space. This gravitational lensing magnifies and distorts the images of distant sources, sometimes producing multiple images of the same background object. Atomic clocks run slightly slower in stronger gravitational fields, an effect that must be corrected for in satellite navigation systems. These phenomena, predicted by Einstein's general theory of relativity, have been verified with extraordinary precision. The bending of starlight during solar eclipses provided the first confirmation in 1919. Gravitational lensing by galaxies and clusters now serves as a tool for studying dark matter and distant cosmic structures. The slowing of time in gravitational fields has been measured using atomic clocks on aircraft and satellites. General relativity describes the behavior of gravity with accuracy that no competing theory can match. The magnetic fields of neutron stars can reach strengths trillions of times stronger than Earth's field. These intense fields arise from the compression of a massive star's magnetic field into the tiny volume of a neutron star during core collapse. Lines of magnetic force that previously spread across millions of kilometers are squeezed into regions only tens of kilometers across, concentrating the field to extreme values. The resulting magnetism produces phenomena unknown elsewhere in nature. Magnetars represent the most magnetic neutron stars, with fields so strong that they can influence atomic structure and produce dramatic bursts of high-energy radiation. The surface of a magnetar experiences forces capable of tearing ordinary matter apart. Yet despite this violence, magnetars remain stable objects, their structure supported by the pressure of degenerate matter against the inward pull of gravity. They represent extreme laboratories for studying physics under conditions impossible to recreate on Earth. The asteroid Ceres, the largest object in the asteroid belt, qualifies as a dwarf planet under current astronomical definitions. Its spherical shape, achieved through gravitational self-organization, distinguishes it from the irregularly shaped smaller asteroids that share its orbital neighborhood. Ceres possesses a thin atmosphere and may harbor substantial amounts of water ice beneath its surface, making it a target of scientific interest for understanding the history and composition of the early solar system. Spacecraft have visited Ceres and returned detailed images of its surface, revealing bright spots that appear to be deposits of salt left behind by evaporating brines. These deposits suggest that liquid water has reached the surface in the geologically recent past, possibly driven by residual internal heat or by impacts that exposed subsurface ice. Ceres represents a transitional object between asteroids and planets, sharing properties with both categories while fitting neatly into neither. The corona of the Sun extends millions of kilometers into space, reaching temperatures of over 1,000,000 degrees, despite being far from the visible surface. This counterintuitive heating remains an active area of research, with mechanisms involving magnetic field dynamics and wave dissipation, proposed to explain how energy reaches the outer solar atmosphere. The corona is visible during total solar eclipses as a pale halo surrounding the darkened disk of the Moon. Solar wind, the continuous outflow of charged particles from the Sun, originates primarily from the corona. This wind streams outward at speeds of hundreds of kilometers per second, carrying magnetic field lines that spiral outward through the solar system. Interactions between the solar wind and planetary magnetic fields produce auroras. While the wind's pressure shapes the boundaries of the heliosphere, the bubble of solar influence that extends far beyond the orbit of Neptune. The resonance orbits of Pluto and Neptune prevent them from ever colliding despite crossing each other's paths. Pluto's orbit carries it inside Neptune's orbit for portions of its 248-year journey around the Sun. Yet the two bodies never approach each other closely because they maintain a 2 to 3 resonance, with Pluto completing 2 orbits for every 3 of Neptune's. This resonance ensures that Pluto always reaches its closest approach to the Sun when Neptune is on the opposite side of its orbit. Many other objects in the Kuiper belt share this same resonance with Neptune, forming a population called Plutinos. The gravitational influence of Neptune during the early solar system apparently captured these objects into resonant orbits that have persisted for billions of years. The resonance provides stability in what might otherwise be a chaotic orbital environment, demonstrating how gravitational relationships can organize cosmic structures over long timescales. The spectra of distant galaxies reveal their compositions, temperatures, and motions through detailed analysis of absorption and emission features. Each element and molecule produces characteristic patterns of dark or bright lines at specific wavelengths, serving as fingerprints that identify the materials present. By comparing observed spectra to laboratory measurements, astronomers can determine what substances exist in objects billions of light-years away. Spectroscopic observations also reveal how fast and in what direction galaxies are moving. The Doppler effect shifts the entire spectrum toward longer wavelengths for objects moving away from us, and toward shorter wavelengths for objects approaching. The magnitude of this shift indicates the velocity, while the direction reveals whether the object is approaching or receding. Nearly all distant galaxies show redshifts, indicating they are moving away as the universe expands. The convective zones within stars transport energy through the bulk motion of hot material. In the Sun, a convective layer occupies the outer third of the solar radius, with hot plasma rising from below and cooler plasma sinking back down. This churning motion produces the granular pattern visible on the Sun's surface, where each granule represents the top of a convective cell, roughly the size of a small country. The energy generated in the core thus reaches the surface through a combination of radiation. Convection plays different roles in stars of different masses. Low-mass stars are convective throughout, with material cycling from core to surface and back. High-mass stars have convective cores, but radiative outer layers. These structural differences affect how elements mix within stars, how magnetic fields develop, and how stars evolve over their lifetimes. The presence or absence of convection in particular regions determines many observable properties of stars. The ice giants Uranus and Neptune differ significantly from the gas giants Jupiter and Saturn, despite their superficial similarities. While all four outer planets possess extensive atmospheres of hydrogen and helium, the ice giants contain much larger proportions of heavier materials, including water, ammonia, and methane. Their blue colors arise from methane in their atmospheres, which absorbs red light and reflects blue. Their internal structures likely include layers of exotic high-pressure ices that behave very differently from ordinary water ice. Uranus rotates on its side, with an axial tilt of approximately 98 degrees, possibly the result of a massive collision during the era of planetary formation. This extreme tilt produces seasons that last decades, with each pole experiencing years of continuous sunlight, followed by years of darkness. Neptune, though more conventionally oriented, possesses the fastest winds in the solar system, with storm systems racing around the planet at speeds exceeding 2,000 kilometers per h-hour. The distribution of matter in the early universe was not perfectly uniform. Tiny fluctuations in density, possibly originating from quantum effects during the first instance, after the Big Bang, provided the seeds around which all subsequent structure formed. Regions with slightly higher than average density attracted additional matter through gravity, while regions with lower density became progressively emptier. Over billions of years, this process produced the cosmic web of galaxies, clusters, and voids that characterizes the modern universe. The cosmic microwave background preserves a snapshot of these primordial density fluctuations, capturing the pattern of slightly warmer and cooler regions that existed when the universe was only 380,000 years old. By analyzing this pattern, cosmologists have determined fundamental properties of the universe, including its geometry, composition, and age. The faint ripples visible in the background radiation represent the origins of all cosmic structure, the seeds from which galaxies and ultimately life eventually grew. The habitable zones of binary star systems can be more complex than those around single stars. If two stars orbit each other closely enough, A planet can orbit the pair at a distance where it receives stable illumination from both suns. If the stars are more widely separated, a planet might orbit one star, while the other provides occasional additional heating. Some configurations remain stable for billions of years, while others lead to ejection or collision within much shorter timescales. Recent discoveries have confirmed that planets can indeed exist in binary systems, orbiting either one star or both. The famous Tatooine of science fiction, with its two suns setting on the horizon, has multiple real-world analogues among known exoplanets. These worlds experience complex patterns of illumination, depending on their orbital relationships with their host stars. Life on such planets would evolve under conditions of variable lighting that might produce adaptations unlike anything found on Earth. The impact history of the Moon preserves a record of bombardment that affected all bodies in the inner solar system. The lunar surface displays craters from impacts that occurred throughout the history of the solar system, with particularly intense bombardment during the first billion years. The absence of erosion or plate tectonics on the Moon has preserved this record, making the lunar surface a natural museum of cosmic violence. Earth experienced the same bombardment history as the Moon, but has erased most evidence through geological activity. The oldest terrestrial rocks date to roughly 4 billion years ago, well after the period of heaviest bombardment. By studying the Moon, we can infer what Earth must have experienced during its earliest epochs, when impacts delivered both destruction and potentially the water and organic molecules that contributed to the emergence of life. The Oort cloud, a hypothetical spherical shell of icy bodies surrounding the solar system at vast distances, may contain trillions of objects. This remote reservoir, extending perhaps a quarter of the way to the nearest star, represents debris from the era of planetary formation that was scattered outward by gravitational interactions with the giant planets. Occasional gravitational perturbations can send Oort cloud objects inward toward the Sun, where they become long-period comets visible from Earth for brief intervals. Before returning to the outer darkness, no spacecraft has ever visited the Oort cloud, and individual objects within it are far too small and distant to observe directly. The cloud's existence is inferred from the orbits of comets that appear to originate from that region. These orbits suggest a spherical distribution of source objects, consistent with the expected scattering history. The Oort cloud remains one of the least explored regions of our solar system. Its population estimated but never counted. The interior structures of terrestrial planets can be probed through seismic observations. On Earth, earthquakes generate waves that travel through the interior and are detected by seismometers worldwide. The speeds and paths of these waves reveal the density and composition of the materials through which they pass. This technique has established that Earth possesses a dense metallic core, surrounded by a rocky mantle, with a thin crust floating atop the mantle's uppermost layers. Mars now has its own seismometer, deployed by the InSight mission, which has detected hundreds of Marsquakes and revealed details of Martian interior structure. The Martian core appears larger and less dense than Earth's, suggesting a different composition. The crust is thicker than anticipated, and the mantle shows unexpected layering. These findings constrain models of how Mars formed and evolved, adding to our understanding of rocky planet development throughout the galaxy. The jets produced by active galactic nuclei can extend for millions of light years, far beyond the boundaries of their host galaxies. These collimated streams of high-energy particles are launched from regions near supermassive black holes, accelerated to near light speed by magnetic fields threading the accretion disk. Once formed, the jets plow through the surrounding medium, heating and displacing gas over volumes that dwarf the visible galaxy. The energy contained in these jets is staggering, capable of influencing star formation and gas cooling throughout entire galaxy clusters. When jets encounter the intracluster medium, they inflate enormous bubbles of hot plasma that can be detected through X-ray observations. These bubbles provide a mechanism for transporting energy from the central black hole to distant regions, potentially regulating the growth of massive galaxies and preventing excessive star formation. The transit timing variations of exoplanets can reveal the presence of additional unseen planets in the same system. When multiple planets orbit a star, their gravitational interactions cause slight variations in the timing of their transits. A planet that would otherwise transit at perfectly regular intervals shows departures from this regularity when tugged by the gravity of companions. By analyzing these variations, astronomers can infer the masses and orbits of planets that may not transit at all. This technique has proven particularly valuable in systems discovered by transit surveys, where only planets with properly aligned orbits are directly detected. Transit timing variations have revealed the presence of additional planets in many systems, sometimes including objects too small to detect through other means. The gravitational interconnection of planetary systems thus provides a tool for discovering worlds that would otherwise remain hidden. The polar ice caps of Mars expand and contract with the Martian seasons, their boundaries advancing and retreating as carbon dioxide freezes from and sublimates into the atmosphere. The northern cap consists primarily of water ice, while the southern cap retains a residual layer of carbon dioxide ice throughout the Martian year. These seasonal changes drive the global circulation of the Martian atmosphere and influence weather patterns across the planet. Beneath the seasonal caps lie permanent deposits of ice that contain a record of Martian climate history. Layered terrains near the poles show alternating bands of ice and dust that may represent cycles of climate change spanning millions of years. Mars has experienced ice ages and warmer periods, with its axial tilt and orbital parameters changing more dramatically than Earth's due to the absence of a large stabilizing moon. The polar deposits preserve clues to this complex climate history. The luminosity function of galaxies describes how many galaxies exist at each level of brightness. Most galaxies are intrinsically faint, with bright galaxies becoming progressively rarer at higher luminosities. This distribution reflects the physics of galaxy formation, with massive galaxies requiring special conditions and more time to assemble. Understanding the luminosity function helps astronomers census the galaxy population and track how galaxies evolve over cosmic time. The luminosity function evolves with redshift, meaning that the galaxy population at earlier times differed from the present-day population. Galaxies were generally smaller and fainter in the early universe, growing through mergers and accretion over billions of years. By measuring luminosity functions at different redshifts, astronomers can trace this evolution and constrain theories of galaxy formation and growth. The isotopic ratios of elements provide information about their nucleosynthetic origins. Different processes produce elements with different relative abundances of isotopes, allowing astronomers to trace which mechanisms contributed to the material we observe today. The ratio of heavy to light isotopes in a sample reflects the temperature and neutron density of the environment where the elements form. Meteorites preserve isotopic anomalies that indicate the presence of freshly synthesized material at the time of solar system formation. Some inclusions contain isotopes that could only have been produced in specific types of stellar explosions, suggesting that such explosions occurred near the forming solar system and contributed material to the planets. The solar system thus bears witness to cosmic events that transpired shortly before or during its birth. The correlation between galaxy mass and central black hole mass suggests a connection between galaxy and black hole evolution. More massive galaxies tend to harbor more massive central black holes, with the black hole mass typically amounting to about 0.1% of the galaxy's stellar mass. This relationship holds across a wide range of galaxy types and sizes, implying that processes governing galaxy growth also influence black hole growth. Several mechanisms might produce this correlation. The same gas that fuels star formation could also feed the central black hole, linking the two growth processes. Alternatively, feedback from the active black hole could regulate star formation, establishing a proportionality between the two masses. The precise mechanism remains uncertain, but the tightness of the observed correlation suggests that galaxy and black hole coevolution is a fundamental aspect of cosmic structure formation. The molecular clouds that give birth to stars contain complex organic molecules that form through surface chemistry on dust grains. In the cold interiors of these clouds, Atoms stick to grain surfaces and react to form molecules that could not assemble efficiently in the gas phase. These surface reactions build increasingly complex structures, eventually producing molecules with dozens of atoms, including amino acids and other biologically relevant compounds. When the cloud collapses to form a star and planets, these molecules are incorporated into the forming bodies. Comets and asteroids, preserving the most primitive materials from the solar nebula, show high concentrations of organic compounds. Delivery of this material to early Earth may have provided the raw materials for the origin of life, connecting biological chemistry to processes occurring in interstellar space long before our planet existed. The planetary nebula phase of stellar evolution lasts only a few tens of thousands of years, a brief interval on cosmic timescales. During this phase, a star that has exhausted its nuclear fuel sheds its outer layers into space, while its core contracts toward its final state as a white dwarf. The ejected material, illuminated by ultraviolet radiation from the hot central star, glows in distinctive colors that reveal its chemical composition. The shapes of planetary nebulae display remarkable variety, from simple spheres to complex multipolar structures. These shapes arise from the interaction between fast and slow stellar winds, magnetic fields, binary companions, and other factors that influence how material is ejected and shaped. Each planetary nebula represents a unique combination of these influences, frozen in place as the material expands and the central star fades. The distribution of dark matter in galaxies forms extended halos that reach far beyond the visible stellar populations. These halos contain most of the galaxy's total mass, with the visible components representing only a small fraction. The halos interact gravitationally with neighboring galaxies and with the cosmic web of large-scale structure, determining how galaxies move and cluster. Mapping dark matter halos requires indirect techniques, since the material emits no light. Gravitational lensing observations reveal the distribution of mass along sight lines to distant sources. Stellar velocity measurements constrain the total mass enclosed within different radii. X-ray observations of hot gas in galaxy clusters trace the gravitational potential wells produced by dark matter. Through these methods, astronomers have built a detailed picture of dark matter distribution on scales from individual galaxies to the largest cosmic structures. The event horizon of a black hole marks the boundary beyond which nothing can escape, not even light. This surface is not a physical barrier, but rather a geometric feature of space-time around extremely compact masses. Objects crossing the event horizon pass the point of no return, inevitably falling toward the central singularity, regardless of their subsequent motion or any forces they might apply. From the perspective of a distant observer, objects approaching the event horizon appear to slow down and redden as gravitational time dilation and wavelength stretching take effect. Light emitted just outside the horizon can escape, but light emitted from inside cannot. The horizon thus acts as a one-way membrane, permitting matter and radiation to enter but never to leave. What happens inside the horizon remains forever hidden from outside observers. Let your thoughts now settle like dust in a quiet room. The cosmic facts you have absorbed tonight require no further action. They exist whether you contemplate them or not, just as the stars continue shining whether anyone watches or not. The universe asks nothing of you in return for its wonders. Feel your breathing slow to the rhythm of a world at rest. The complexity of galaxies, the patience of starlight, the gentle drift of planets through their orbits, all of these continue without your supervision. You can release any remaining tension and allow sleep to approach on its own schedule. The darkness of space is not empty but full of potential, a canvas upon which light paints its endless variations. The darkness of your room shares this quality, offering a space where rest can bloom without interference. You are surrounded by the same fundamental forces that shape the cosmos, the same gravity that holds galaxies together, the same quantum fields that give matter its properties. If you remain awake, let the remaining words carry you closer to the boundary of sleep. There is no urgency. The night stretches before you with the patience of interstellar distances. Each breath brings you closer to rest. Each moment of relaxation deepens the peace that surrounds you. The gentle rhythm of celestial mechanics governs the motion of every object in the universe. Planets follow their orbits with mathematical precision. Moons circle their parent worlds according to the same laws, and even the most distant galaxies rotate in patterns determined by the distribution of mass within them. This cosmic choreography unfolds continuously, requiring no conductor, no external guidance, only the fundamental properties of gravity and motion that have operated unchanged since the beginning of time. Consider the elegance of orbital motion. An object in orbit is constantly falling toward the body it circles, yet its sideways motion carries it past the point where it would otherwise crash. The result is a continuous curved path that repeats endlessly, a balance between falling and moving that requires no energy expenditure to maintain. Satellites in orbit around Earth follow this principle, as do planets around the Sun and stars around galactic centers. The same physics applies everywhere, from the smallest moon to the largest galaxy. The oldest light in the universe has been traveling for nearly 13.8 billion years. This ancient radiation released when the cosmos was only a few 100,000 years old has been stretched by the expansion of space until it now appears as faint microwave radiation, rather than the visible glow it once possessed. Every direction you look, this primordial light streams toward you, a relic of an era when the universe was smaller, denser, and hotter than it is today. This cosmic microwave background represents the earliest snapshot of the universe that we can directly observe. Before this light was released, the cosmos was opaque, filled with a plasma so dense that photons could not travel freely. When the universe cooled enough for atoms to form, the plasma cleared and light could finally stream through space, unimpeded. That moment of clearing, called recombination, released the radiation that still fills the cosmos today, a whisper from the dawn of time that surrounds us on every side. The surfaces of some worlds remain utterly unchanged for billions of years, without atmospheres to carry wind or rain, without liquid water to erode landscapes, without geological activity to reshape terrain. These worlds preserve features from their earliest epochs. Craters formed by ancient impacts remain sharp and distinct, their rims unweathered, their floors undisturbed. Walking on such a surface would mean walking across ground that has remained essentially the same since before life existed on Earth. Mercury provides an example of such preservation. Its surface bears the scars of bombardment from the solar system's earliest eras, craters overlapping craters in patterns that record billions of years of impact history. The planet has no atmosphere to speak of, no water, no plate tectonics. Changes occur only through additional impacts or subtle thermal effects. What exists on Mercury's surface today closely resembles what existed there 3 or 4 billion years ago, a landscape frozen in geological time. The spiral structure of galaxies arises from density waves that propagate through their stellar disks. These waves do not consist of the same stars moving together, but rather represent patterns through which stars pass, like ripples crossing a pond. As stars enter a density wave, they slow slightly and crowd together, enhancing the density of the region. As they exit, they spread apart and resume their normal spacing. The wave itself propagates at a different speed than the stars, maintaining a persistent spiral pattern. This explanation resolves a puzzle that troubled astronomers for decades. If spiral arms consisted of the same stars always moving together, the differential rotation of galaxies would wind them tightly within a few 100 million years. Yet, spiral galaxies display their characteristic patterns over timescales of billions of years. The density wave theory explains this persistence by treating the spirals as patterns rather than physical structures, allowing galaxies to maintain their elegant forms across cosmic time. The temperature at the center of the Sun reaches approximately 15 million degrees Celsius. At these extreme temperatures, hydrogen nuclei move so rapidly that they can overcome their electrical repulsion and fuse together, releasing energy in the process. This nuclear fusion powers the Sun's luminosity, converting roughly 600 million tons of hydrogen into helium every second. The energy released deep in the core gradually works its way outward, eventually escaping from the surface as the light and heat that warm our planet. Despite this continuous conversion, the Sun contains enough hydrogen to maintain its current output for another 5 billion years. The mass involved in fusion represents only a tiny fraction of the Sun's total hydrogen supply. Stars are remarkably efficient machines, extracting energy from matter through processes that will sustain them for durations that dwarf all of human history. The Sun that rises tomorrow will be essentially identical to the Sun that set today, unchanging on any timescale relevant to human experience. The void between galaxies contains almost nothing, yet it is not truly empty. Scattered atoms of hydrogen, perhaps 1 per cubic meter on average, drift through these immense expanses. Faint magnetic fields thread through the intergalactic medium, too weak to affect most processes, but present nonetheless. Photons from distant sources stream through continuously, carrying information about their origins to any detector that might intercept them. The void is less a complete absence than a profound thinness, an extreme dilution of the matter and energy that concentrate elsewhere. These intergalactic spaces make up most of the volume of the observable universe. The galaxies that capture our attention represent only a small fraction of cosmic real estate, dense islands in an ocean of near emptiness. Light traveling from one galaxy to another may journey for millions of years without encountering any significant matter. The isolation of galaxies from one another provides a kind of cosmic privacy, allowing each to evolve according to its own internal processes without immediate influence from its neighbors. The rotation of neutron stars can be extraordinarily rapid, with some completing hundreds of rotations per second. These collapsed stellar cores, containing more mass than the Sun compressed into spheres, only tens of kilometers across, spin with speeds that seem impossible for objects of their size. The surface of a rapidly rotating neutron star moves at a significant fraction of the speed of light, generating powerful magnetic fields and beaming radiation across space. Such rapid rotation arises from the conservation of angular momentum during stellar collapse. When a massive star's core collapses, any rotation it possessed becomes concentrated into a much smaller volume, dramatically increasing the spin rate. A star that rotated once per m-onth might produce a neutron star that rotates many times per second. This amplification of rotation represents one of the most dramatic examples of angular momentum conservation in the natural world. The colors visible in nebulae arise from specific atomic transitions in the gases that compose them. Hydrogen, when excited by ultraviolet radiation from nearby stars, emits a characteristic red glow at a wavelength of 656 nanometers. Oxygen produces both green and blue emissions at different wavelengths. Other elements contribute additional colors, creating the rich palettes visible in astronomical images. These colors represent the fingerprints of the elements, revealing their presence and conditions without any need for physical sampling. The physics underlying these emissions is remarkably simple. When an electron in an atom absorbs energy, it jumps to a higher energy level. When it falls back down, it releases a photon with a wavelength determined by the energy difference between the levels. Each element has its own unique set of energy levels, and therefore its own unique set of emission colors. The cosmos displays its chemistry through light, painting its clouds with the signatures of the elements they contain. The orbital velocities of planets decrease with distance from the Sun, following a pattern discovered by Johannes Kepler in the early 17th century. Mercury, closest to the Sun, races along its orbit at nearly 48 kilometers per second. Earth moves at a more moderate 30 kilometers per second. Neptune, far in the outer solar system, creeps along at only 5.4 kilometers per second. This progression reflects the weakening of solar gravity with distance and the corresponding reduction in orbital speed needed to maintain stable orbits. This relationship between distance and velocity holds throughout the cosmos, governing the motion of stars around galactic centers, galaxies around cluster cores, and indeed any object orbiting any other. The mathematics of gravity produces consistent results regardless of scale, from the motion of artificial satellites around Earth to the orbits of stars around supermassive black holes. The universe operates according to principles that apply everywhere, without exception or variation. The zodiacal light visible before dawn and after dusk represents sunlight scattered by interplanetary dust. This faint glow, extending along the ecliptic where the planets orbit, has been observed and wondered at since ancient times. The dust particles that produce it are microscopic, remnants of comets and asteroid collisions that spread throughout the inner solar system. When the sun's light strikes these particles, some of it bounces back toward Earth, creating a diffuse luminosity that can be seen from dark locations. This dust represents debris from the ongoing processes of the solar system, material that never quite settled into permanent homes on planets or moons. It slowly spirals inward toward the sun, replenished by fresh material from cometary tails and collisions. The zodiacal light thus reveals the dynamic nature of interplanetary space, a realm where particles drift and scatter under the influence of solar radiation and gravity. Far from empty, the space between planets contains countless tiny fragments of the solar system's continuing evolution. The habitable zone concept has evolved considerably since its initial formulation. Early definitions focused solely on the distance from a star at which liquid water could exist on a planetary surface. More recent considerations include atmospheric composition, planetary albedo, tidal locking, and a host of other factors that influence surface conditions. A planet might lie within the traditional habitable zone, yet remain hostile to life due to factors not captured by simple distance calculations. Conversely, some bodies outside traditional habitable zones might support life in unexpected ways. Moons of giant planets warmed by tidal heating rather than stellar radiation could maintain liquid water far beyond the nominal habitable zone. Planets with thick hydrogen atmospheres might trap enough heat to remain warm at distances where thin atmosphere worlds would freeze. The concept of habitability has grown more nuanced as our understanding of planetary diversity has expanded, revealing possibilities that simple models could not anticipate. The brightness of stars as seen from Earth depends on both their intrinsic luminosity and their distance. A nearby dim star may appear brighter than a distant brilliant one, making apparent brightness a poor guide to true stellar properties. Astronomers distinguish between apparent magnitude, which describes how bright a star looks, and absolute magnitude, which describes how bright it would look from a standard distance of about 33 light-years. This distinction allows meaningful comparison of stellar properties, regardless of their actual locations. Sirius, the brightest star in the night sky, owes its prominence partly to its proximity, lying only about 8.6 light-years from Earth. Canopus, the second brightest, is much more luminous intrinsically, but appears dimmer because it lies roughly 310 light-years away. Rigel, fainter still in apparent brightness, actually produces more light than either Sirius or Canopus, but lies so far distant that its apparent brightness suffers accordingly. The night sky presents a projection of three-dimensional stellar distributions onto a two-dimensional sphere, blending near and far into a single visual field. The gravitational influence of planets extends far beyond their visible surfaces. Each planet carries with it a gravitational well that affects the motion of anything passing nearby. Spacecraft approaching planets must account for these gravitational effects, which can be used to accelerate or redirect trajectories through maneuvers called gravity assists. The Voyager probes used this technique repeatedly, gaining speed from encounters with Jupiter and Saturn that allowed them to reach the outer solar system and beyond. These gravitational spheres of influence overlap and interact throughout the solar system. The precise motion of any object depends on the combined gravitational pulls of all nearby bodies, creating a complex dynamical environment that requires sophisticated calculations to navigate. Yet despite this complexity, the underlying physics remains simple. Every mass attracts every other mass, with a force proportional to their masses and inversely proportional to the square of the distance between them. This single law governs all gravitational phenomena, from the fall of raindrops to the orbits of galaxies. The spectral classification of stars organizes them according to their surface temperatures and colors. The sequence O, B, A, F, G, K, runs from the hottest, bluest stars to the coolest, reddest ones, with additional categories for even cooler objects. Each letter corresponds to a range of temperatures that determines the appearance of the star's spectrum, including which absorption lines appear strongest and which colors dominate the overall emission. This classification system reveals fundamental properties of stars through nothing more than analysis of their light. An O-type star is not only blue but also massive, luminous, and short-lived. An M-type star is not only red but also small, dim, and extraordinarily long-lived. The sequence thus captures correlations between observable properties and underlying physical characteristics, allowing astronomers to infer much about a star's nature from relatively simple observations. The phases of planetary moons follow the same logic as the phases of Earth's moon. A moon's illuminated hemisphere always faces the sun, but from a given viewing position, different fractions of that hemisphere may be visible. As a moon orbits its planet and the planet orbits its star, the geometry continuously changes, producing cycles of waxing and waning brightness. These cycles have been observed and recorded for many moons throughout the solar system, each following patterns determined by its orbital parameters. Galileo's observation of the phases of Venus provided crucial evidence for the heliocentric model of the solar system. If Venus orbited Earth as Ptolemaic astronomy suggested, it could never show a full set of phases. But if Venus orbited the Sun, it would display all phases as its position relative to Earth, and the Sun changed over time. The observed phases matched the heliocentric prediction, helping to overturn centuries of geocentric thinking. The simple geometry of illumination thus contributed to one of the most profound revisions in scientific understanding. The atmosphere of Titan, Saturn's largest moon, is denser than Earth's atmosphere, despite Titan's much lower gravity. This thick envelope of nitrogen, methane, and organic compounds creates surface pressure roughly 50% higher than at sea level on Earth. The atmosphere supports weather systems including rain, clouds, and wind, though the precipitation consists of liquid methane and ethane rather than water. Rivers and lakes of hydrocarbons carve channels and fill basins across Titan's frigid surface. Titan represents one of the most Earth-like bodies in the solar system, despite its frigid temperatures and exotic chemistry. The presence of a substantial atmosphere with active weather distinguishes it from most other moons. The organic chemistry occurring in its atmosphere and on its surface has drawn scientific interest as a possible analog for prebiotic processes that might occur elsewhere in the universe. Titan demonstrates that complex atmospheric and chemical systems can develop far from the warmth of any star. The alignment of stars in constellations is coincidental rather than physical. Stars that appear close together in the sky often lie at vastly different distances from Earth, with no actual relationship beyond their apparent proximity. The constellation Orion provides a familiar example. Its stars range in distance from a few hundred to over 1,000 light-years, scattered through a volume of space that would require centuries to cross at the speed of light. From another location in the galaxy, these same stars would form entirely different patterns. The constellations we recognize are artifacts of our particular vantage point in space. Ancient observers, unaware of stellar distances, naturally grouped bright stars into patterns and associated those patterns with mythological figures and stories. These groupings served practical purposes for navigation and calendar, keeping even though they carry no physical significance. The patterns persist in modern star maps as convenient reference frames, dividing the sky into regions that astronomers still use for locating celestial objects. The temperature variations across planetary surfaces depend on many factors including rotation rate, atmospheric density, and axial tilt. Planets that rotate rapidly experience smaller temperature differences between day and night because the exposure time is too short for extreme heating or cooling. Planets with thick atmospheres retain heat more evenly, reducing the contrast between illuminated and dark hemispheres. Planets with significant axial tilts experience pronounced seasonal variations, as different hemispheres receive more or less direct sunlight over the course of an orbit. Mercury demonstrates the extreme effects of slow rotation and no atmosphere. Its day-night cycle lasts about 176 Earth days, providing ample time for the sunlit side to heat to over 400 degrees Celsius, while the dark side cools to nearly -200 degrees. This temperature range exceeds that of any other planet in the solar system, a consequence of Mercury's unique combination of proximity to the Sun, slow rotation, and lack of atmospheric insulation. The structure of elliptical galaxies differs fundamentally from that of spiral galaxies. While spirals possess flattened disks with organized rotation, ellipticals appear as smooth, rounded systems with stars orbiting in random orientations. This difference reflects their formation histories. Spiral galaxies form from gas that settles into rotating disks before collapsing into stars, while ellipticals often result from mergers that randomize stellar orbits and deplete gas reservoirs. The stellar populations of ellipticals are typically older than those of spirals, with less ongoing star formation. This reflects the absence of gas from which new stars could form. Ellipticals contain predominantly red and yellow stars, the survivors of ancient stellar generations, while spirals display the blue colors of young, hot stars mixed with the older populations. The color difference between galaxy types thus reveals their distinct evolutionary pathways and current states of stellar activity. The transit method for detecting exoplanets relies on measuring tiny dips in stellar brightness when planets pass in front of their host stars. These dips amount to only a fraction of a percent for Earth-sized planets around Sunday-like stars, requiring extremely precise photometry to detect. Despite this challenge, the transit method has proven extraordinarily successful, discovering thousands of exoplanets since its first successes in the early 2000s. The depth of a transit reveals the size of the transiting planet relative to its star. A larger planet blocks more light and produces a deeper dip. The duration of the transit provides information about the orbital period and distance. Repeated transits confirm the planetary nature of the signal and refine the orbital parameters. Through careful analysis of transit light curves, astronomers have characterized planets ranging from massive gas giants to rocky worlds smaller than Earth. The chemistry of cometary coma reveals the composition of material preserved from the early solar system. As a comet approaches the Sun and its surface warms, volatile substances sublimate into gas that surrounds the nucleus in a diffuse envelope. Spectroscopic analysis of this coma reveals water, carbon dioxide, carbon monoxide, methane, ammonia, and a variety of more complex molecules. These materials represent the chemical inventory of the region where the comet formed, preserved through billions of years in the cold outer solar system. Comets thus serve as chemical time capsules, carrying samples of the primordial solar nebula into the present. Some of the molecules detected in cometary coma are precursors to the building blocks of life, including amino acids and other organic compounds. The delivery of such materials to early Earth through cometary impacts may have contributed to the emergence of life, connecting the chemistry of comets to the origin of biology. These ancient wanderers carry not only ice and rock, but also the raw materials from which living systems could develop. The Lagrange points of the Earth Sunday system represent locations where the gravitational and centrifugal forces balance to allow stable or semi-stable orbits. The most famous of these points, L2, lies about 1.5 million kilometers from Earth. On the side opposite the Sun, spacecraft positioned there can remain in the Earth's shadow while maintaining a fixed position relative to both Earth and Sun, making it an ideal location for space telescopes that need stable thermal environments. The James Webb Space Telescope occupies this L2 point, using its position to keep its mirrors cold enough to detect faint infrared radiation from the distant universe. Other spacecraft have occupied various Lagrange points for different purposes, taking advantage of the unique orbital dynamics these locations offer. The existence of such points demonstrates the richness of three-body gravitational systems, where the interplay of multiple gravitational sources creates structures that would not exist around isolated masses. The magnetic fields of some planets flip polarity over geological timescales. Earth's magnetic field has reversed hundreds of times during the planet's history, with north and south magnetic poles trading places over periods of thousands of years. These reversals leave traces in volcanic rocks that record the field direction at the time of cooling. By studying these traces, geophysicists have reconstructed the history of Earth's magnetic field going back hundreds of millions of years. The mechanism driving these reversals involves the complex fluid dynamics of Earth's outer core. Convection currents in the liquid iron generate the magnetic field through dynamo action, but the precise behavior of these currents can shift over time, eventually triggering a reversal. During a reversal, the field may weaken and become disordered before re-establishing itself with opposite polarity. The timescales and patterns of reversals are irregular, defying simple prediction. Yet the overall phenomenon is well established through abundant geological evidence. The ring systems of giant planets display remarkable diversity in their structures and compositions. Saturn's rings are bright and broad, composed primarily of water ice particles, ranging from dust grains to boulder-sized chunks. Jupiter's rings are dark and dusty, barely visible even to spacecraft in the Jovian system. Uranus and Neptune possess intermediate ring systems with unique characteristics reflecting their individual formation and evolutionary histories. The rings of Saturn extend across distances comparable to the separation between Earth and the Moon, yet their thickness amounts to only tens of meters in most places. This extreme flatness results from collisions between ring particles that gradually damp out vertical motions while preserving the overall rotation. The rings are not solid structures, but rather swarms of independent particles, each following its own orbit around the planet. Their apparent solidity emerges from the collective behavior of countless objects too small to resolve individually. The surface gravity of different celestial bodies spans an enormous range. Earth's surface gravity provides the baseline against which other bodies are often compared. The Moon's surface gravity is only about 1/6 of Earth's, allowing astronauts to bound across its surface in ways impossible on our planet. Jupiter's surface gravity, if such a thing could be said to exist for a gas giant, would be about 2.5 times Earth's. Neutron stars possess surface gravities billions of times stronger than Earth's, capable of crushing any ordinary matter that might approach. These variations in surface gravity affect everything from the mechanics of walking to the retention of atmospheres. Low-gravity bodies struggle to hold onto light gases, which escape into space over geological timescales. High-gravity bodies trap even the lightest elements, building up thick envelopes that may never dissipate. The distribution of atmospheres throughout the solar system reflects the interplay between surface gravity, temperature, and the history of volatile delivery and escape. The ecliptic plane, defined by Earth's orbit around the Sun, serves as a reference for describing positions in the solar system. Most planets orbit within a few degrees of this plane, a legacy of the flat disk of gas and dust from which the solar system formed. The orderly arrangement of planetary orbits near the ecliptic contrasts with the more spherical distributions of objects in the outer solar system, where gravitational perturbations have scattered bodies into all orientations. Pluto's orbit provides a notable exception to the near-ecliptic rule among major bodies, tilting about 17 degrees from the ecliptic. Many Kuiper belt objects share this inclined character, their orbits having been disturbed by Neptune's gravitational influence during the solar system's youth. The scattered disk and Oort cloud populations show even greater orbital inclinations, their members distributed in a roughly spherical shell around the Sun, rather than concentrated near the ecliptic plane. The luminosity of galaxies evolves over cosmic time as their stellar populations age and their star formation rates change. Young galaxies rich in gas and actively forming stars shine with the blue light of hot, massive stars. As galaxies deplete, their gas and star formation declines. Their light becomes dominated by older, cooler, redder stars. The overall luminosity often decreases as the most luminous stars burn out and are not replaced. This evolution is visible directly in observations of distant galaxies, which show us the universe as it appeared billions of years ago. By comparing the properties of galaxies at different distances, and therefore different cosmic epochs, astronomers can trace how the galaxy population has changed over time. The youngest visible galaxies appear smaller, bluer, and more irregular than their modern counterparts, reflecting the vigorous star formation and frequent interactions that characterized the early universe. The principle of equivalence, a cornerstone of general relativity, states that the effects of gravity are indistinguishable from the effects of acceleration. An observer in a closed room cannot tell whether the room is sitting on the surface of a planet or accelerating through empty space at the same rate. This equivalence has profound implications for our understanding of gravity, leading to the geometric interpretation in which massive objects curve the fabric of space-time and objects move along the straightest possible paths through that curved geometry. Tests of the equivalence principle have achieved extraordinary precision, confirming Einstein's insight to many decimal places. Objects of different composition fall at exactly the same rate in gravitational fields. As expected, if gravity couples universally to all forms of mass and energy, any departure from exact equivalence would require revision of general relativity, but no such departure has ever been detected. The principle stands as one of the most precisely verified aspects of our fundamental physical theories. The stellar wind from the Sun extends outward to form the heliosphere, a vast bubble of solar influence that encompasses all the planets and extends far beyond Neptune's orbit. Within this bubble, the solar wind dominates the interstellar medium, carrying magnetic field lines and charged particles outward from the Sun. At the boundary of the heliosphere, the solar wind slows and interacts with the galactic environment, creating complex structures that spacecraft have begun to explore. The Voyager probes have now crossed the heliopause, the boundary, where the solar wind gives way to interstellar space. Their instruments detected the transition through changes in the particles and magnetic fields they encountered, confirming that they had entered a new environment. These spacecraft thus became humanity's first ambassadors to interstellar space, carrying records of human civilization into a realm that will take tens of thousands of years to traverse at their current speeds. The age dating of rocks through radioactive decay provides the most reliable method for establishing absolute chronologies in geology and planetary science. Each radioactive isotope decays at a characteristic rate described by its half-life, the time required for half of any initial quantity to transform into daughter products. By measuring the ratio of parent to daughter isotopes in a sample, scientists can calculate how long the decay has been occurring, and therefore the age of the sample. Different isotopes with different half-lives are suitable for dating materials of different ages. Carbon-14, with a half-life of about 5,700 years, works well for organic materials up to tens of thousands of years old. Uranium isotopes, with half-lives measured in billions of years, date the oldest rocks on Earth and the meteorites that predate planetary formation. This range of tools allows construction of chronologies spanning from historical times to the birth of the solar system. The orbital mechanics of multi-planet systems can produce complex patterns of motion over long timescales. Gravitational interactions between planets cause their orbits to precess, with the orientation of each orbit gradually rotating over millions of years. These precession cycles can interact with each other, producing quasi-periodic variations in orbital eccentricity and inclination that play out over timescales of hundreds of thousands to millions of years. In the Earth system, these orbital variations influence climate through their effects on the distribution of solar radiation across the planet's surface. The eccentricity of Earth's orbit varies over cycles of roughly 100,000 years, while the tilt of Earth's axis varies over cycles of about 41,000 years. These Milankovitch cycles correlate with the timing of ice ages, demonstrating how astronomical factors can drive climatic changes on Earth. The planets, through their gravitational interactions, reach across space to influence conditions on our world. The detection of biosignatures in exoplanet atmospheres represents one of the most anticipated goals of astrobiology. Certain combinations of atmospheric gases, such as the simultaneous presence of oxygen and methane, could indicate biological activity, since these gases would otherwise react and disappear. Detecting such disequilibrium would not prove the existence of life beyond Earth, but it would provide strong circumstantial evidence worthy of intense follow-up investigation. Current and planned space telescopes are developing the capabilities to detect biosignatures on potentially habitable exoplanets. The James Webb Space Telescope can analyze the atmospheres of some exoplanets during transits, identifying absorption features that reveal the presence of specific molecules. Future missions may achieve the sensitivity needed to detect biosignature gases in the atmospheres of Earth, like planets orbiting nearby stars. The search for life beyond Earth thus moves from speculation to observational science. The proper motion of stars across the sky amounts to only tiny angular displacements even over centuries of observation. The fastest moving star visible from Earth shifts its position by only about 10 arcseconds per year, an angle too small to detect with the naked eye even over a human lifetime. Most stars move far more slowly, their apparent positions essentially fixed from one generation to the next. This near immobility gave rise to the ancient concept of the fixed stars, in contrast to the wandering planets. Modern astrometric techniques can detect proper motions far too small for visual observation. Precise measurements of stellar positions over decades reveal motions of milliarcseconds per year for many stars, corresponding to velocities of kilometers per second at typical stellar distances. These motions, though imperceptible to casual observation, accumulate over cosmic timescales to produce significant changes in stellar distributions. Given enough time, the familiar constellations will deform and eventually become unrecognizable. The reflectivity of planetary surfaces determines how much incoming radiation is absorbed versus reflected. Dark surfaces absorb more energy and warm to higher temperatures, while bright surfaces reflect more energy and remain cooler. This principle applies across scales from local terrain features to entire planetary surfaces, influencing climate patterns and driving weather systems through differential heating. The albedo of a planet, its overall reflectivity, plays a crucial role in determining its equilibrium temperature. Earth's albedo of about 0.3 means that roughly 30% of incoming solar radiation is reflected back to space. Changes in albedo, whether through variations in cloud cover, ice extent, or vegetation, can produce climate feedbacks that amplify or moderate initial temperature changes. The interplay between albedo and temperature creates complex dynamics that climate scientists work to understand and model. The distribution of impact craters on solid surfaces provides information about the age and geological history of those surfaces. Older surfaces accumulate more craters over time, reaching saturation states where new craters on average destroy as many old craters as they create. Younger surfaces, formed by volcanic activity or other resurfacing processes, display fewer craters corresponding to the time elapsed since their formation. This crater counting technique has been applied throughout the solar system, from the heavily cratered highlands of the Moon to the surprisingly fresh surfaces of some outer solar system moons. Enceladus, a small moon of Saturn, shows regions with virtually no craters, implying geological activity that has resurfaced those areas in the geologically recent past. The contrast between heavily and lightly cratered regions on the same body reveals the spatial and temporal patterns of geological activity. The stellar mass function describes the distribution of masses among newly formed stars. This distribution appears remarkably consistent across different star-forming regions and different environments, suggesting that universal processes govern stellar birth. Most stars are born with masses well below that of the Sun, with massive stars becoming progressively rarer at higher masses. Only a small fraction of stars reach the massive extremes that produce supernovae and neutron stars. This mass distribution has profound implications for the evolution of galaxies. Massive stars, though rare, produce most of the heavy elements and most of the high-energy radiation in the universe. Their short lifetimes mean they quickly return their enriched material to the interstellar medium through stellar winds and supernova explosions. Low-mass stars, though contributing less to chemical enrichment, persist for timescales that exceed the current age of the universe, accumulating in galaxies over cosmic time. The magnetosphere of a planet interacts with the solar wind to create a complex boundary layer between planetary and interplanetary environments. On the day side, the solar wind compresses the magnetosphere, pushing the boundary inward toward the planet. On the night side, the magnetosphere stretches outward in a long tail extending millions of kilometers away from the Sun. This dynamic interaction varies with solar activity, expanding and contracting as the pressure of the solar wind fluctuates. Within the magnetosphere, charged particles become trapped in radiation belts that can pose hazards to spacecraft and astronauts. Earth's Van Allen belts, discovered in the late 1950s, contain high-energy protons and electrons concentrated in toroidal regions around the planet. The intensity of these radiation belts varies with solar activity, swelling during geomagnetic storms and subsiding during quiet periods. Understanding the dynamics of radiation belts has become essential for protecting space assets and planning crewed missions beyond low Earth orbit. The phenomenon of gravitational lensing allows distant objects to be magnified and distorted by foreground masses. Strong lensing produces multiple images or dramatic arcs when the alignment is precise enough. Weak lensing produces subtle distortions in the shapes of background galaxies that can only be detected statistically. Both forms provide information about the distribution of mass in the lensing objects, including dark matter that cannot be detected through its light emission. Microlensing, the transient brightening of a background star when a compact object passes in front of it, has been used to detect planets, brown dwarfs, and even isolated black holes. The duration and shape of the brightening event reveal the mass and velocity of the lensing object. This technique can detect planets that produce no transit or radial velocity signatures, expanding the census of exoplanets to include objects that would otherwise remain hidden. The internal structure of stars can be probed through astroseismology, the study of stellar oscillations. Stars ring like bells, with waves of compression and expansion traveling through their interiors and producing subtle variations in brightness. The frequencies and patterns of these oscillations depend on the internal structure of the star, allowing astronomers to infer properties of stellar cores that would otherwise remain inaccessible. This technique has revolutionized our understanding of stellar interiors, providing information about core rotation, chemical mixing, and evolutionary state. Stars that appear similar in surface properties may show very different oscillation patterns, revealing differences in their internal structures that reflect different evolutionary histories. Astroseismology has also enabled precise measurements of stellar radii and masses, improving our ability to characterize the planets that orbit those stars. The origin of heavy elements through rapid neutron capture occurs in environments of extreme neutron density. In these settings, atomic nuclei absorb neutrons faster than they can decay, building up extremely neutron-rich isotopes that subsequently undergo beta decay to produce stable heavy elements. The R process, as this mechanism is called, produces roughly half of all elements heavier than iron, with the other half coming from slower neutron capture in stellar interiors. The primary sites of our process nucleosynthesis have been identified as neutron star mergers, cataclysmic events, where two neutron stars spiral together and collide. Observations of gravitational waves and electromagnetic radiation from such an event in 2017 provided direct evidence for our process element production. The light from the merger site showed spectroscopic signatures of freshly synthesized heavy elements, confirming decades of theoretical prediction about the origin of materials like gold and platinum. The structure of the cosmic web, the largest scale organization of matter in the universe, reflects the initial conditions established in the first moments after the Big Bang. Galaxies and clusters are not distributed randomly, but instead trace filaments and sheets that surround vast, empty voids. This pattern grew from tiny density fluctuations present in the early universe, amplified by gravity over billions of years to produce the structures we observe today. Simulations of cosmic structure formation can reproduce the observed patterns, with remarkable fidelity. Starting from realistic initial conditions and following the physics of gravity and hydrodynamics, these simulations produce virtual universes that statistically match observations. The success of these simulations demonstrates that the physics governing structure formation is well understood, even as details of galaxy formation within the cosmic web continue to challenge modeling efforts. The composition of planetary atmospheres is not static, but evolves through processes that operate over a wide range of timescales. Volcanic outgassing adds new material to atmospheres while atmospheric escape removes it. Chemical reactions among atmospheric species produce new compounds while consuming others. Biological activity, where it exists, can profoundly alter atmospheric composition over geological timescales. Earth's atmosphere has changed dramatically over its history, with early reducing conditions giving way to the oxidizing environment that now supports aerobic life. The Great Oxidation Event, roughly 2.4 billion years ago, saw atmospheric oxygen rise from trace levels to significant concentrations, irreversibly altering the chemistry of both atmosphere and surface. Similar events may have occurred on other worlds, and detecting their atmospheric signatures could reveal past or present biological activity. The thermal emission from planets and moons reveals their internal heat budgets and surface conditions. Objects that receive little solar radiation may still emit detectable infrared radiation if they possess internal heat sources such as radioactive decay or tidal heating. The temperature inferred from thermal emission provides information about the energy balance of these bodies and the processes occurring within them. The giant planets emit more energy than they receive from the Sun, a signature of their ongoing contraction and internal heat production. Jupiter radiates roughly twice as much energy as it receives, while Saturn radiates nearly 3 times as much. This excess emission reflects the gradual cooling and contraction that has continued since these planets formed, releasing gravitational potential energy as thermal radiation over billions of years. The phenomenon of stellar occultation occurs when a foreground object passes in front of a star, temporarily blocking its light. These events provide precise measurements of the size and shape of the occulting body, revealing details that would otherwise be impossible to observe. Occultations by asteroids have mapped their regular shapes, while occultations by planets with atmospheres produce gradual dimming that reveals atmospheric structure. Occultations by small outer solar system objects have discovered rings around Chariklo, a minor body only about 250 kilometers across. This unexpected finding demonstrated that ring systems can form around objects far smaller than the giant planets, challenging assumptions about the conditions required for ring formation. Occultation observations continue to reveal surprises, demonstrating the value of this technique for studying objects too small and distant for direct imaging. The spectral energy distribution of astronomical objects describes how their emitted energy is distributed across wavelengths. Stars emit most of their light at wavelength corresponding to their surface temperatures, with hot stars peaking in ultraviolet and cool stars in infrared. Galaxies display composite spectra reflecting the mix of stellar populations and interstellar material they contain. Active galactic nuclei show distinctive features from their accretion disks and jets. Fitting observed spectral energy distributions with models allows astronomers to infer physical properties of the emitting objects. The temperature, luminosity, and composition of stars can be determined from their spectra. The star formation history, dust content, and stellar mass of galaxies can be estimated from their integrated light. These techniques extract remarkable amounts of information from the photons that reach our detectors. The zone of avoidance refers to the region of the sky obscured by the dust and stars of our own galaxy. Observations at optical wavelengths cannot penetrate this zone, leaving a gap in our maps of the extragalactic universe. Radio and infrared observations can see through the dust, revealing galaxies that would otherwise remain hidden, but optical surveys must contend with this fundamental limitation. The zone of avoidance approximately follows the plane of the Milky Way, where dust concentrations are highest. This band across the sky hides roughly 20% of the extragalactic universe from optical view. Important structures, including portions of the Great Attractor that influences the motion of nearby galaxies, lie behind this obscuring band. Multi-wavelength observations are essential for constructing complete pictures of the local cosmic environment. The cooling of white dwarf stars proceeds so slowly that the oldest white dwarfs in the galaxy have not yet cooled significantly. These stellar remnants, composed of degenerate matter that supports itself through quantum mechanical pressure, radiate their residual heat into space over billions of years. The cooling rate decreases as the temperature drops, extending the cooling timescale for older, cooler white dwarfs. White dwarf cooling curves provide independent estimates of the ages of stellar populations. By measuring the luminosities of the faintest white dwarfs in a cluster, astronomers can determine how long ago that cluster formed. This technique has been applied to globular clusters and the galactic disk, providing age estimates consistent with other methods. The coolest white dwarfs thus serve as cosmic chronometers, their faintness a measure of the time elapsed since their progenitor stars died. The phenomenon of frame dragging arises from the rotation of massive objects, which carry space-time along with them as they spin. Near a rotating black hole or neutron star, this effect becomes significant, forcing nearby particles into orbits that precess in the direction of the central object's rotation. Frame dragging represents one of the most striking predictions of general relativity, demonstrating that mass in motion affects the geometry of spacetime differently than mass at rest. Experimental verification of frame dragging near Earth has been achieved through precise measurements of satellite orbits and gyroscope precession. The effects are tiny, requiring exquisitely sensitive measurements to detect, but they match the predictions of general relativity with impressive accuracy. These measurements extend our confidence in general relativity to regimes that could not be tested through astronomical observations alone. The search for extraterrestrial intelligence has employed radio telescopes to scan the sky for artificial signals. The reasoning behind this approach is straightforward. Radio waves travel at the speed of light and can be produced efficiently with technology, making them a natural choice for interstellar communication. A civilization wishing to announce its presence could broadcast signals detectable across galactic distances with transmitters of reasonable power. Despite decades of searching, no confirmed extraterrestrial signals have been detected. This null result could mean that technological civilizations are rare, that they do not broadcast in ways we can detect, or simply that we have not yet searched thoroughly enough. The vastness of the galaxy ensures that even extensive searches have covered only a tiny fraction of the possible signal space. The search continues with improved instruments and refined strategies. The dynamics of galaxy clusters reveal the presence of dark matter through the motions of their constituent galaxies. Galaxies within clusters move at velocities that exceed what the visible mass could gravitationally bind. Without additional unseen mass, these galaxies would fly apart, dispersing the cluster over cosmic timescales. The presence of dark matter, inferred from these excessive velocities, provides the gravitational glue that holds clusters together. X-ray observations of hot gas in clusters confirm and extend these dynamical measurements. The gas, heated to millions of degrees by gravitational compression, emits X-rays that reveal its temperature and distribution. From these observations, the total mass required to confine the gas can be calculated, and once again, it exceeds the visible mass by a factor of several. Multiple independent lines of evidence converge on the same conclusion. Clusters are dominated by dark matter. The phenomenon of stellar polarization arises when light from a star passes through dust grains aligned by magnetic fields. The elongated grains preferentially absorb light polarized along certain directions, imprinting a polarization signature on the starlight that reveals the orientation of the magnetic field along the line of sight. By mapping polarization across the sky, astronomers can trace the magnetic field structure of the galaxy. This technique has revealed that the galactic magnetic field follows the spiral arms, with field lines generally aligned parallel to the arm directions. Variations in polarization direction and magnitude reveal local departures from this average pattern, indicating the complex and turbulent nature of interstellar magnetism. These fields, though weak by laboratory standards, influence the motion of cosmic rays and the formation of stars throughout the galaxy. The end states of massive stars depend sensitively on their initial masses and compositions. Stars below a certain mass threshold end as white dwarfs, their cores supported by electron degeneracy pressure above this threshold. But below another, neutron degeneracy pressure can support the core, producing neutron stars. Above the highest threshold, nothing can prevent complete gravitational collapse, producing black holes. The precise mass limits separating these outcomes are subjects of ongoing research. The upper limit for white dwarfs is well established at about 1.4 solar masses, the Chandrasekhar limit. The upper limit for neutron stars is less certain, lying somewhere between 2 and 3 solar masses, depending on the poorly understood equation of state of ultradense matter. Stars in the uncertain region may produce neutron stars, or black holes depending on the details of their explosions and the amount of material that falls back onto the remnant. The phenomenon of tidal disruption occurs when a star passes too close to a massive black hole. The gravitational gradient across the star exceeds the star's self-gravity, tearing it apart into a stream of gas that stretches around the black hole. A portion of this material falls inward, forming an accretion disk that brightens dramatically before fading over months to years. These tidal disruption events provide rare glimpses of dormant black holes that otherwise reveal no observable activity. Observations of tidal disruption events have increased dramatically with the advent of wide-field time domain surveys. These events illuminate the demographics of massive black holes in galaxies, where no other tracers reveal their presence. They also probe the physics of accretion in extreme conditions, with the sudden arrival of large amounts of material producing outbursts that test models of disk formation and jet launching. The cosmic expansion carries galaxies away from each other at rates proportional to their separation. This relationship, first observed by Edwin Hubble in the 1920s, established that the universe is not static but expanding. The rate of expansion, the Hubble constant, has been measured with increasing precision over the decades, though tensions between different measurement methods suggest that our understanding may still be incomplete. The expansion of space differs from ordinary motion through space. Galaxies are not flying apart through a fixed background. Rather, the space between them is stretching, carrying the galaxies along with it. This distinction has important consequences for understanding the observable universe, including the fact that objects beyond the cosmic horizon are receding faster than light due to the expansion of intervening space. Now allow your thoughts to grow quiet like the space between galaxies. The information you have absorbed tonight will remain with you, but it requires no further attention. Let the complexity of the cosmos simplify into a single feeling of peace. The universe continues its vast operations without any need for your wakefulness. Feel your body settle more deeply into rest. The same forces that hold planets in their orbits hold your molecules together. The same quantum principles that govern stellar fusion govern the chemistry of your cells. You are made of the same materials as the stars, temporary configurations of matter and energy that will one day return to the cosmic pool from which they emerged. The darkness that surrounds you resembles the darkness between stars, a peaceful emptiness in which light travels patiently toward destinations it will reach only after immense spans of time. Your journey towards sleep follows a similar path, unhurried and inevitable, governed by rhythms as regular as the orbits of planets. Let each breath carry you closer to the threshold of dreams. The cosmos asks nothing of you except perhaps a moment of wonder at its scale and patience. Tomorrow the sun will rise as it has risen for billions of years, and you will wake refreshed by sleep. But for now, let go of waking concerns and allow yourself to drift. The facts you have heard tonight will remain true whether you remember them or not. The galaxies will continue their slow rotations, the stars will continue their nuclear burning, and the planets will continue their endless circuits. None of this requires your supervision. You can release your attention and allow sleep to claim you. If you are still awake, let these final words serve as gentle companions on your journey toward rest. The universe holds countless more wonders than any single night can explore. Other journeys await on other nights, each one offering new paths through the cosmic landscape. For now, this particular journey approaches its end. The soft glow of distant stars represents not chaos but order, not violence but patience. The cosmos appears peaceful from our perspective because its timescales so greatly exceed our own. Changes that would seem dramatic if witnessed in moments unfold over eons, becoming essentially invisible to creatures who live for mere decades. This cosmic patience can become your own. There is no urgency in sleep, no deadline that must be met. The transition from waking to dreaming happens on its own schedule, governed by biological rhythms that have evolved over hundreds of millions of years. Trust these rhythms as the planets trust gravity, following paths that have been traced countless times before. Your bed cradles you like a moon held in orbit by gentle gravitational forces. The blankets that cover you represent insulation against the cold of night, just as atmospheres insulate planets against the cold of space. You are protected, supported, and safe within your small corner of the cosmos. Let your eyes grow heavy if they have not already closed. Let your muscles release any remaining tension. Let your mind grow quiet like a nebula waiting for stars to form within its depths. The stillness that approaches is not emptiness but potential, a state of rest from which new energy will emerge. The last thoughts of the night can be simple ones. The stars are distant. The universe is old. Time moves slowly on cosmic scales. You are small against this immense backdrop, yet you are also woven into its fabric, made of its materials, subject to its laws. This connection is neither burden nor obligation, but simply fact, a context for existence that requires no response. Sleep now and dream of distant worlds if dreams come. Or let sleep be dreamless, a pure rest without narrative or image. Either way, the cosmos continues its patient unfolding, and you will wake to find it essentially unchanged, ready to share more of its wonders whenever you wish to listen. The journey ends here, but others will begin. Thank you for spending this time among the stars. May your rest be deep and peaceful. Good night.